Hello, and a warm welcome to everyone. My name is Zita.
And I am Farah. We will be your MCs for today. Before we get started, do let us know via the chat box if you have any audio or visual issues. Our tech committee will try to help you. Also, we request that you change your Zoom profile name to your full name so we can address you with your actual name during the Q&A session. For your information, to avoid interruptions, everyone logging in is muted and their video is disabled by default. And when applicable, participants will be unmuted or their video will be enabled. Nonetheless, you may communicate via the chat box.
Thank you for joining us for the Bioinformatics Workshop Fiesta, or BWF Colloquium, an inauguration event of the Fiesta. The colloquium is co-located with the Malaysian Youth Bioinformatics Symposium 2.0, organized by Perdana University together with Multimedia University. For your information, BWF is a joint effort involving the Association for Medical and Bioinformatics Singapore, MYBS in short, Asia Pacific Bioinformatics Network, AP Bionet in short, and Perdana University, Malaysia.
BWF aims to expand bioinformatics skills and competencies in the Asia-Pacific community and beyond. MYBS is working towards the same goal locally in Malaysia. There are other such similar local efforts in the region and more needs to be done. The BWF series offers a plethora of 16 workshops of choice with a proposed pathway. For more information, do visit the BWF website. The links are also provided in the Zoom chat box right at the top. Without further ado, we would like to proceed with the welcome address. We call upon Dr. Muhammad Asif Khan, the President of AP Bionet, to give his address on behalf of the BWF Working Committee.
Thank you. Excuse me. Thank you, Zita and Farah. Let me just quickly share my screen. All right. So hello and a warm welcome to one and all. Thank you for taking the time on a Saturday. I know it's a big toll for many. So thank you for sparing the time on a Saturday to join us for this event. And representing the BWF Working Committee, comprising of AP Bionet, MYBS, Perdana University, there are three key messages that I would like to share. First, kudos to the organizing team for making this event happen. The team is largely made up of undergraduate and some postgraduate students. And for many of them, this is perhaps their first time organizing such an event of this scale. We strongly believe in providing students with opportunities for training and exposure. And we hope this was an enriching experience for all of them. Secondly, I want to give a quick history of BWF. The first BWF was successfully started and completed in 2018 with 9 back-to-back workshops, 1 per month. And this was actually in collaboration with our partner, Universitas YRC in Indonesia. Back then, actually, we did it in a different way, different from today. It was the classical way, face-to-face interaction with the participants, and we still managed to attract more than 190 registrations for all. That's the total for all the 9 workshops. We also had a colloquium back then, which was attended by about 60 plus participants. So we wanted to repeat this success in 2020 by bringing it to Singapore. And then, as you all know, COVID-19 happened, and that changed everything. However, instead of, on one hand deciding to cancel the plan, we decided to take up the challenge and wanted to go virtual and offer it to a much broader audience, which is something we have always wanted to do, but this felt like, the perfect time to do so. Of course, and today is the outcome of that effort. And this outcome is both exhilarating and intimidating at the same time. So this map you see here speaks volume. We have close to 700 registrations for the colloquium alone, which is way beyond the earlier number of 60. So this is really, heartwarming to see that many people are interested from different parts of the world. You can see the numbers there. So we thank all of you who have taken the time to do this. And for some of you, this may be a little odd hour. Some of you may still be very early in the morning. So it is exhilarating because this was a dream. It was a dream to reach out to such a large number at a single event. And at the same time, it's intimidating because this is our first. And of course, we are worried that things will go wrong here and there. And so I'm going to apologize in advance for any shortcomings on our side during the course of the event today. The third point I want to highlight is that BWF is a joint effort, and it aims to grow bioinformatics skills and competencies in the community. We offer a series of 16 workshops of a choice. We have a path where we actually break down the workshops into essential, beginner, intermediate, and advanced, so people can start off wherever they feel more comfortable, and those who are really new or just are starting, they can start right at the beginning with the essential and go all the way to the advanced workshops. And so we have also, for the instructors of the workshops, we actually have advertised across the region, so we can we aim to get the best instructors to be facilitating the workshops. We got a very good response. We are working with them to finalize the schedule for the workshops, and we hope to release the schedule very soon. And we hope many of you who are participating today would actually partake in the workshops eventually, the first one starting next month. So do look out for our future announcements. With that, I thank everyone for joining today. I hope you have a blast and have fun and learn a lot from the session today. I thank everyone involved in making this happen, and not forgetting our workshop instructors, our keynote speakers, and plenary speaker, who also have taken time to speak to you today and share their wealth of knowledge. Thank you very much. Zita and Farah, I pass it back to you.
Thank you, Dr. Asif. Next, we call upon Dr. Yam Waikit, Acting Dean of Perdana University, School of Data Science, representing the Perdana University, as the main host of MYBS 2.0 to deliver her welcome address.
Hi, good morning, everybody. I hope you can hear me. If you could, maybe just give me a thumbs up. Cool. Thank you so much. So, hi, welcome to this event. So, on behalf of the university, we would like to thank all of you to be here. Again, like what mentioned by Prof. Asif, that is a bit unique in the sense that, we are doing it virtually. But I'll see this as a new normal, and I think that this is a new way for all of us to embark in this journey. So, before that, I want to thank the organizing committee for this event for able to pull everything in a very, very short time. And just mentioned by Prof. Asif that this is very unique in a sense that it was initially planned to be a physical event, but because of the current condition, it has changed into a virtual condition. So a lot of things has changed, but I'm so happy that the team is very versatile and they are ready to move and make the event to be a success. So thank you very much for the team. And I think I'm not going to talk more about BWF because Prof. Asif already mentioned, but I'm happy to share from a Perdana University point of view that this BWF bioinformatics workshop Fiesta has been a project. It's like our baby for our university, and with just one aim to be able to go around to train people with various fields in bioinformatics, and we have done it successfully in 2018, 2019 as well. So this year, initially the plan was to do it in Singapore physically. However, because of the current situation, but I do not see it as something bad. I think this is great in the sense that it becomes virtual and we can involve many other people around the world. So, well, we take opportunity of current situation, and I feel that this is the right way that we are moving forward. So, good job to the team. So, just let me briefly talk about bioinformatics. After all, we are here for a reason. Bioinformatics is such an exciting field, yeah, that it focuses on interdisciplinary fields. So if you check on, your friends who are in another field, they probably very much focus into a specific topic. But bioinformatics students are trained in various fields, ranging from biology to computer science, mathematics and statistics, and even many more. So you can see that we are actually at two different, very, very wide spectrum of the field that we are at. And this has become students to be very, very versatile. Yeah, so I always mention to students that, being versatile is important in the current setup because we are no longer moving into a silo, but we are all moving into an interdisciplinary kind of world. So it's so important that we are trained in different perspectives. And if you see the current trend, not only that bioinformatics is so important, but how big data has come into this perspective. And in this current world where we're in this big data and also data science, we can see that bioinformatics are like forerunners because they are trained in looking into data, and not only look into data but also transform them into to be informative information. So, and this kind of technique is so important currently in this current setup. And therefore, because of that, I think as a graduate in bioinformatics, we should be proud of ourselves that we are doing this. We are actually at the forefront, and this is the part that we come in. But however, coming from a university point of view, I strongly believe that it's so important that you have a continuous learning attitude. That is why the university's continuous effort is that we wanted to train people in this field. Having just a graduate, having just a bachelor degree in bioinformatics perhaps is insufficient. From time to time, we need to learn, we need to upskill ourselves. Therefore, in our university, we are always, very active in providing the opportunity not only for students but also for researchers, or even for those who are working at various stages of your career, that we train you at different level. So, like for example, in Perdana University itself, we have formal programs ranging from undergraduate to postgraduate, and that commitment of doing that education is supported by even giving scholarships, discounts, and also financial aids who wanted to be in that field. So those are formal programs, but we also have a lot of informal programs where we allow you to have training from time to time to upskill yourself. Therefore, it's so important, to be in this network and to learn from time to time. So we actually encourage those active participation, yeah, between associations and societies. Therefore, the connection is important, the networking is important. Having an event like today, I think this is a very good thing that we are all connected and we can learn so much more from each other. So with that, I want to thank all of you, and again, I want to wish you all the best, and I wish that you have a good time today in today's event. Thank you very much.
Thank you, Dr. Yam. Last but not least, we welcome Ms. Shalini to say a few words as a voice of the student community.
Thank you, Ms. Farah and Ms. Zita. A big welcome to all of the participants, speakers, and instructors. Thank you for joining us today. I am Shalini Kumar, the chair of the MYBS 2.0 organizing committee. I thank the opportunity to say a few words on behalf of the student community. Events such as these are vital to the student community, which provide a unique opportunity for all of us to meet people from our field of interest, to share knowledge and experiences. Indeed, there is nothing more exciting than meeting new people, hearing their stories, and being inspired. In the current COVID-19 pandemic, this has become more difficult, but we are grateful of the virtual platforms that allow us to continue to engage with others, albeit a little differently. Nonetheless, the challenges of this new norm bring along new opportunities. For example, 8 months ago, I did not imagine that I will get to attend a bioinformatics event together with 600 plus other participants from different parts of the world. Come to think of it, it does feel surreal, at least to many of us students who are more used to the classical way of teaching. I would like to take this opportunity as well to say a few words as a student of Multimedia University. We students of the Faculty of Information Science and Technology in Multimedia University had the honor to organize the first MYBS in November last year. We didn't expect there will be another MYBS this year because of the pandemic. We would like to thank Perdana University for inviting us to co-organize MYBS 2.0. We hope that another university will consider to continue this with us in the future. And I think the future looks bright for bioinformatics and data science students with the rising demand for more people with the skills and competencies to manage and mine data. I am pleased to have MYBS tie up with BWF in support of the systematic training program that has been planned ahead for one whole year starting next month. As for today, we have a great live program and I hope it will be fun and full of learning for all of you. And I made to understand that we may have some surprise announcements. Please do look out for them. Have fun and all the best. Thank you. So let's pass back to Farah and Zita.
Thank you, Shalini. We also want to acknowledge the effort and contributions of our partners, National Supercomputing Centre Singapore and Altaco Sdn Bhd. We thank both organizations. With that, we conclude the welcome ceremony. Declare the event formally open and hope that you enjoy and benefit from the program plan. Our first bioinformatics activity for the day will be 2 workshops that will be run in parallel. The first workshop is entitled Biomolecular Visualization, which will be delivered by Dr. Choi Si-Bing. Dr. Choi is an associate professor at Perdana University and the chief executive officer of Altaco Sdn Bhd, a local bioinformatics startup. With a degree in biochemistry from University of Malaya, she pursued further studies with a Master in Information Technology and PhD in Pharmaceutical Technology from University of Science Malaysia. Besides varied research experience, she was the facilitator for international students from University of California, San Diego, United States, Osaka University, Japan, Indian Institute of Technology, Delhi, India, Chulalongkorn University, Thailand, and many more. And many more prestigious universities around the world under the Pacific Rim Application and Grid Middleware Assembly Program. Prior to her appointment at Perdana University, she was a research scientist at Malaysian Institute of Pharmaceuticals and Nutraceuticals, IPharm, and a postdoctoral research fellow at the School of Industrial Technology, USM. Her expertise include protein structure prediction, membrane molecular dynamic simulation, and in silico high-throughput screening, as well as structure and ligand-based drug discovery. Of late, she has been making a mark in other areas of bioinformatics.
The second workshop is entitled Healthcare Data Analytics, which will be delivered by Dr. Kenneth Ban Kim. Dr. Kenneth obtained his Bachelor in Biochemistry and MBBS degree from the National University of Singapore and a PhD in Cancer Biology from Stanford University. He completed his postdoctoral training in mouse carrier genetics and at the Institute of Molecular and Cell Biology, IMCB, Singapore, before joining the Department of Biochemistry at NUS 2011. He also serves as the Program Director for Life and Biomedical Science at the National Supercomputing Centre, NSCC. His research and education interests are in cancer genetics, high-performance computing, for precision medicine and bioinformatics education. He is currently the elected president of the Association for Medical and Bioinformatics Singapore, MYBS. That was a brief bio-sketch from the illustration career of the true instructors. Some housekeeping announcement before we begin the workshops. All relevant links for the program today, including the workshops, are available in the welcome letter which was emailed to you. If you did not get them, and you are here because someone shared the link with you, you may want to check your spam mailbox because it has the other key information for today. By the way, you can also access the Open Broadcast YouTube channel link from our BWF and MYBS websites or the links provided in the Zoom chat box. Please use the chat box sparingly, only for questions and if you need any help. Also, we kindly request again that you change your Zoom profile name to your full name so we can address you with your actual name during the Q&A session. With that, we now hand over to the instructors and we'll be back for some housekeeping message at the end of the workshop sessions. Have fun all.
All right, thanks very much. Thanks for the introduction. Very happy to be part of this inaugural BWF 2020 session. This, as Professor Asif Khan mentioned, this is something new, the new normal for us. And we're happy to be able to reach out virtually to many more. So, okay, let me get started by sharing screen. All right. Okay, so maybe just as out of interest, I have a polling input on. So if just to break the ice, if anybody wants to tell us where you're from, you just go to this website, pollev.com/BWF2020. All right, so I can see there's a huge representation from Malaysia, and Johor is very well represented also. It appears to be a separate country, right? No, I did not specify whether it was a country or not. Happy to have people from Indonesia and Philippines joining us as well. All right, so with that, I will start asking some other questions just to make sure that we're on board so that we can get started. All right. So I think the first thing is that this set of tutorials actually runs on a Docker system. This was actually done because we wanted some of the things that you're going to be doing so that you can run it on your own computer. Now, there are many ways to do this one. The simplest way is actually we run it on the server. But we realized from some previous workshops that we've conducted that most people actually want a local copy so that they are able to run things themselves and experiment. Most oftentimes, once the server is shut down, then you are left with just a static material. So with this spirit, we hope if most people can get this installed, and if we can't get it installed now, don't worry, the instructions there, we'll modify them accordingly and see whether we can get you started. But I won't delay this anymore if some of you already have installed, so you can walk through with us. All right, so why do we actually choose this system? This is like almost what we call a lightweight virtual machine. All right, so most of you, if you have, for example, a Windows machine or Mac machine, most of the bioinformatics tools actually run on another operating system called Linux that we'll talk about briefly. And the issue is that unless you actually delete this and actually install Linux on your machines, it's very hard to have a local copy to run it. But that changed with the availability of virtual machines. So you could have a Windows machine, you could have a Mac machine, and you run a virtual machine, and you can actually run Linux on there. And some of you may have tried before. You can use virtual blocks to actually install different versions of Linux to play around and start learning about that. So that would be a gateway to a lot of bioinformatics analysis. Now, how this is different is because the VM here actually is quite heavy, in a sense that it's quite large, and sometimes it's harder to distribute the material in workshops. So Docker is something else that was invented to actually solve this problem. So in this case here, we do not have a very heavy VM virtual machine layer, but it's something a bit more lighter called Docker Engine. So we don't have to replicate each operating system here. So it's very lightweight. We can package different applications in a nice container so that later some of you that have installed and actually pulled it down, are able to run Linux, and we have an environment that everybody knows that it works. All right, so that's the rationale for actually trying this. It's the first time you're doing it, so so your feedback would be very much appreciated after the workshop. All right, so with that, let me move over to the screen. All right, so I'm looking also at the chat sessions. Okay, before that, maybe I move to the other poll just to make sure that we do have an idea of the level of familiarity, right? So it also helps me to decide whether I should go faster or slower. All right. All right, so just a quick poll so that I can gauge my pace. Okay, heard of it? Okay, good, excellent. All right, so I noticed the numbers may be very small, so I may not be representative, but I think hopefully this gives an idea of interactivity in the new normal using Zoom. All right, cool. Most of you are familiar, so we can get started. Okay, some of you said what's Linux, all right? So it's an operating system that's distinct from Windows and Mac, and the difference is actually it's open source and free. Okay, great. So with that, then the first thing you need to do, if you have followed instructions, is actually you open your command line. So in Mac, you can use a terminal. In Windows now, I think it's command share. So there are a few commands to get it working. So for example, in the instructions, there was an instruction to actually run the container that's going to contain all the necessary applications for us to go through this workshop. All right. So if you have done that, I won't show it now because some of you may have run it already. So the point here is once you run the thing, actually the local application is stored on your machine. So you can put commands such as Docker. So PS, what processes are there, and then -a is show me everything. So if I click on that on my desktop, it says that, okay, I have something running here. All right, the image is called Portainer, which is another application. I've not run the workshop one yet. All right, and then it tells you other things such as whether it's open any ports or not. So you may imagine this is a separate machine inside your machine, and it's usually isolated, but sometimes you can open little ports so that you can access it. All right, so we'll run that. So the instructions recall, it was this, which was Docker run. Okay, so we're going to run the thing, and then after that, -d means run it in the background. Then after the option called -p here, -p is actually opening the port. So let me just explain to you. So this one will pull an image down, and it pulls it down from the website called Docker Hub, and it's my repository. So BWF workshop, and it brings it down into your computer. Then after that, we can run it. Now this -p option says that there is a local server running inside port 8888, and then colon means you want to expose it outside, okay? So this is outside here. This is your actual desktop or laptop. And basically opening a port, and this port that's exposed is the one that we will connect to through our web server. All right, so let me run this one. Now, when you run this, basically you get a whole bunch of numbers here. So this one is the unique identifier. It's a very long string to ensure basically that there's no duplication. So this one is just the ID. Now we can see whether it's running or not by doing the same thing. I can put Docker PS or process and -a to see what's happening. Okay, so lo and behold, we can see that the container now, which is from this repository here, is actually running already. It's been up for 24 seconds and it's open a port. So this is inside here and this is outside. So later we're going to access it on our local machine through port 8888. All right, okay, so that's all you need to know for now, and this is all isolated. Now we're going to move into the container, so we don't have to see this anymore. All right, cool. So so also before we paste everything, let me go to the next question. Whether how familiar are you with this? I think some of you may be familiar, and this workshop is slightly more healthcare focused. So we're going to look at an example where someone actually sequenced himself, is a doctor, sequenced himself and members of his family, and trying to see whether he could explain something that his family was experiencing, and they identified something. All right, okay. So good, some of it. So remember, this is a familiar word thing, so I'll paste it. So some of you are somewhat familiar, so okay. So I'll try and paste myself accordingly. All right, cool. So now over here, while the poll is happening here, I'll put it on this side. And let's open a browser. And the address to put is 127.00.1 and then colon 8888, meaning that this one will actually connect to your local server. So remember, the Docker container now is running. It is as a small little server with all the applications that are necessary for variant calling. That's it running there, and then now we are just connecting to it through our browser. All right, so here I will just put here, so you type 127.0.0.0 as in instructions, and then port 888. All right, now it's port 88. Then if I run it, you will see this, and this basically says that, okay, the server is alive, it's running the Jupyter Lab notebook, and you need to put in a password. So as in instructions, a password is BWF2020. Okay, I just put here, it's BWF2020. All right. Okay, so you log in, and then you will have this notebook. So right now, this is our system now. Everything lives inside. Is running in a container on your machine. Okay, so let me just put this aside first, and then let's see this. Okay, most of you are somewhat familiar. Okay, excellent. Okay, I will switch to the, oops, sorry. Okay, I'll switch to the next poll. So you can ask questions on the group chat. The other way also is posting questions here that I'll try and monitor along the way. All right, may not be able to answer them immediately, but we'll see. Okay, I'll put this on this side, and then while we continue with this. Okay, let me just change the size, and so some of you may have seen this one. Actually, it looks exactly as what if you had installed this thing called Anaconda. All right. So Anaconda is a very nice package distribution, and actually packages a lot of Python and other modules together, and you are able to install it on the machine. Now we have to do a Docker container because many of the tools that we use in bioinformatics are not really available in Anaconda. All right. Okay, so let's orientate you with this. So this one, you have a toolbar up here, just like a familiar operating system, opening a file, running, and other things that I'll describe shortly. This one is a notebook system, okay, that we'll use to conduct our lesson. And then the other one is actually opening a terminal. Okay, so we need to pull some lessons in. Now on the left-hand side here is a sidebar here that tells you whether there are any files or folders. All right, it's empty, meaning there are no lessons here. So we need to pull the lesson down. Okay, so if you open this one on the terminal, notice here that this thing here is actually running Linux on your machine. All right, so now we're in a Linux environment connected through the browser. Okay, so what do we need to do? Okay, so we need to get the lessons down. Now, the way the lessons were designed, they were put into this repository called GitHub. All right, so This one could be another part of the workshop where we talk about something called version control, meaning that we can develop things, and as we develop it further, we can make changes to it and it will track everything for us. So right now, I know I was changing the lessons, trying to make it up to date, and everything was tracked. So I use this system so that you can get the latest down here. All right, so now we need to pull it down. So the instruction is git clone, and then I will type this address. So it's github.com, and then it's my repository, Kenneth Ban, and then BWF2020.git, git. All right, so now hold on. So it will pull down the latest version of the lesson. But in the meantime, let me make it easier to see. Okay, it's all one word here. Okay. Let's make it easier to see. All right. All right. So let me also paste this into the chat so you can just copy and paste. All right. The chat is here. Oops, sorry. Let me see. I post it to everybody in the meeting. All right, so you should be able to see that, and then you just copy the whole thing. I'll leave it down here as I go here. So as I was talking, it was downloading the entire lesson plan. So notice what is different now. What's different now is there's a new folder called BWF2020. All right. Okay, let me check. No, I don't think there are any questions now. It's activated. Okay, cool. All right, so now we are done with the terminal already. Okay, so the fun thing about it is that once you have this container now, it's isolated in the system. No matter what you do inside this thing, it's not going to destroy your other parts of your computer setup. Okay, so now we click on this folder here, BW20, to enter here. So I can drag this to see what it is. Now there are two folders here. So getting started is just an introduction to Linux. So for those of you who are familiar already, don't worry, go have a cup of tea or something like that. All right, chill out, stretch your legs. And then after that, we'll shortly move into the workflow for aligning, variant calling. And the interesting part is actually the annotation, where we're trying to find meaning from any disease variant that we are finding. Okay, so right now you just click the first one, the first folder, getting started. And you can see this symbol here. This is just an icon for saying that it is a notebook. Okay, this is your familiar thing. This is a folder and then some files here. But we're going to open this thing. The extension is called IPYNB. It is short for IPython Notebook. So this system was initially developed as originated as IPython, and then it was made more versatile and has been rebranded as JupyterLab. Okay, so if I click on this, we will open this folder. So now we're going to learn our stuff in this notebook here. So if everybody can see, so we're going to have a preamble to Linux. All right. So for those of you who are not familiar, it's a chance for you to just go around. So I think the first thing we'll learn is actually knowing where we are. All right, or listing the contents of a directory. So we can do that by actually using the command ls. Now so what we can do is that notice here, over here is actually a bar saying that where your current state of execution is. And you want to move forward, you just press play here, then we advance. Now notice that why is it advancing? Now if I double click on this, actually this one is editable. This is where I annotate the thing, so we can a mixture of text as well as things that we execute. All right, so here you're free to change or add anything here. So for example, this is my own private notebook. Okay, and then after that, notice here that this is called a cell. Okay, everything here contains a cell, and there are different types of the cell. It is either code, markdown, or raw. So if markdown means you can put text images there also. So if I press play here, it will render it as though it's like HTML like that. All right, so it's a markdown format. So you can add your own notes here. So let me just delete that. Okay. And then I run this again, and then we get that. All right, so I'm just, so you can read along saying that we'll start looking contents of the file system, and we'll use the command ls. Now when you reach here, if you want to execute it, you got two ways to do it. You can press this play button here, or you can just put shift enter. All right, okay, shift enter. Okay. Now over here, on your left-hand side, you have a benefit of the bar. So it auto updates anything, any change in the folder over here. So you notice that when I put ls, it lists, for example, here, the notebook system, the image, and then the image. So if you look on this side, it's actually just a reflection here. All right. So for those of you not familiar, Linux commands, actually you can extend it by looking at what options that you can stipulate. So this is a very simple output, and sometimes it's hard to read. And you can have options such as -L, the long format, -A, they are hidden files. Usually we don't really touch them, okay, unless we have a specific purpose. And then the one that's useful also is -H, where some of the file sizes are actually not hard to read. So let me click on this. So I execute ls -H, and then we have the listing of the directory. All right. Now, good thing about that code execution is we can just change it and see what happens. So if I just put -L, then I can see that the difference here is the file sizes are just in numeric form. So it's sometimes hard to read where the, how big the size of the file is. So let's go back and put -H, and then we have that. All right. Now, those of you who don't know, have not much exposure to Linux, you will see on this left-hand side here, it looks quite strange. There are many symbols, minus sign, there's R, W, and sometimes you see X down there. All right. So this one, just to demystify the process, in case you later, if we see the contents of the directory, the way it's done is actually, this is a very short form to delineate who has permissions to read, write, or execute, and whether it's a directory or not. So what we can see here is the way you read it is on the left-hand side first. If it's just a minus, it's a regular file. If there's D, later we'll see it means it's a directory. And then the first three groups here, R, W, or X, tells you that that's permission of the owner. So you're the owner of the system. So you have full rights, read, writing, and executing. Then after that, you can also have this thing, what we call a group designation. Okay, maybe it's your group of friends, group of teammates, or lab mates like that. So the next three here will tell you that, okay, if it's RW minus means in that group you can read, write, but none of them can execute. Only the owner can execute it, right? And then the last one is other people, O for others, right? So this one is R minus minus. So the way we read it from left to right is the owner, okay, and then the group people, and then others like that, okay? Okay, so sorry, UGO. The user, you are the one, and then the group, and then others. All right. So this one means only you can do the reading, group cannot, and then this one, others, you can't access it. All right. Okay, so you can read more of my explanation here. So I'll go through a bit more quickly because most of you are familiar with this. Okay, cool. Now, next thing is that we need to know where we are, because later when we see the files like that, we can get lost. So Linux is a hierarchy structure, actually same for Mac and Windows also. So you start with this thing called a slash. In Windows, they conventionally use a slash as the other way, all right? But by convention now, since we are inside this container system, it's running Linux, and then we start here. So everything starts from the slash here, and then if you want to traverse all the way here, you just go slash, the next one is home, then slash, the next one go to Tom, slash, there's a document folder like that. So we use this convention actually to get to the file that we want if it's actually somewhere else. All right, cool. So to find out where we are, so actually I'm not sure where we are in this notebook here. So you can use the command pwd. All right, so I go here and I execute it. Okay, so we are in the folder which is home slash BWF2020. Then after that slash the folder is getting started folder. All right. Yeah. Now some quick notes about creating, changing, or deleting directories. So let's create a directory within here. So when we do it, let's observe what happens on the left hand side. All right. Okay, so the command is mkdir or make directory. Execute this. And you wait a few seconds, you should be able to see something popping out here. All right. If not, then we refresh it. So over here, you can see the directory is created, and then we can see what's there. Okay. Again, as I said, when we do the ls command here, it's actually reflecting what we see on this side. Okay. So, but this one gives you more details. For example, what the permissions, forgot, this is the user, this is the group that you belong on. So notice that the user is root, meaning that you have full access to the system here. You can install stuff within here inside the container. You can do whatever you want. You can delete a lot of things also. But I won't encourage that because if not, this workshop will end prematurely. Okay. So we can see that the listing of the new directory here, yeah, it's this one here. You can see that it starts with a letter D, so it indicates that this is a directory. Okay, the next command that I want to learn is cd, which is changing directory. So we can type change directory, go inside, and then we list once we are inside already. How do we know we're inside? Okay, so I can add another cell. This one means I want to create another execution cell. I put here, and then why don't I just type the command pwd? Then I can see where I am. So now it's not just stopping here. Now it has gone further, and now it's inside the my directory. Now we know where we are. We make a listing. What do you think we'll see? Okay. Well, we'll see nothing because it's just an empty directory. All right. So let's play around and let's create an empty file. So we can use the command touch here to just create. So I just say create a file called my file. So let me execute that. Nothing happened, but so we'll have to do the ls command to see if anything has changed. So now we are still inside the directory, and it is I created the thing called my file at this time here with these permissions. All right. So now how do we get out? So to go backwards, we use the 2 dots. Right. It's like backtracking. So if I do that, all right, let me add another cell here, and then let's see where we are now using the PW. Every time you're not sure where you are, I just put PWD, because sometimes when I'm moving around directories, when I'm saving stuff, I forget where I am. All right, so now it is the home BWF01, and then, but getting started is no longer inside my directory. Okay. Okay, double confirm. You do a listing again, and indeed we are out. All right. If you want to see what's inside the directory, all you do is just put the name of the directory right after the ls command. So if I put ls minus directory, you will see that I'm listing the contents inside my directory directly, rather than trying to go inside then after the listing it. All right. Okay, so let me clean up this because I don't want this empty this folder. All right. So we can use a command called remove directory, rm directory. Okay, and oops, it failed. Okay, the reason is that you can only remove an empty one. So we can actually try and remove it in 2 ways. We can go into the directory, remove the file, come out, and then delete it. All right. Okay. So, or we can just remove the file since we know what it is. So we can do remove my directory. Then it goes into the file. All right. So let me show you something nice about a notebook. We are actually now running inside the Linux bash kernel. You can see on the right hand side. Okay. The notebook is very versatile because you can have different kernels. So if you have this one, we can have the Python kernel, we can have the R or Python here, and then the notebook would execute these commands. And now we have also Julia. All right. Okay, so now let's go back to this. So notice here, if I put the command rm, I want to delete something. So I say my directory, I can just put my, and I press tab, it will auto-complete for you. So this one I can't remember. And then I want to remove this one. All right. And then let's have a look at the directory now, whether anything is inside. Nope, total is 0. And then we go ahead and remove it. Okay, now there are no errors now because the directory is empty. Let's confirm that. And yes, lo and behold, there's only the images directory, but no my directory anymore. Okay. All right. So for those of you who are not familiar, I think I just explained the concept of input output and this thing called redirection of piping, because we use this when we analyze the sequence later. Now, it's easier maybe if I explain using the diagram. So basically, any program here can accept input, all right? You can have a text file, you can type things in like that. Then the program will come out with 2 outputs. The usual output is standard outs, all right? But if there's an error, sometimes it will come out as standard error. Now, assuming that things go wrong, you standard out, then you have a choice of whether to pass, you can pass it to another program to continue execution, or you want to save the contents out into a file. All right, so this symbol, the greater than sign, is what we know as redirection. And then this vertical bar, this is not number 1, okay? This is not number 1. No. This is a pipe symbol or pipe operator that we can pass it along. So this is the strength of the Unix system concepts that were pioneered in the 1960s and 70s, where you can have programs that do something, the output can be passed to another one. And you can imagine you can chain it to another one and another one like that. So that's the power of this thing, all right? It sometimes flows well with our thinking of how we process data. Okay, so let's illustrate this. Okay, so to do this, I will try and execute a program that will give me a standard out, all right? So one of the programs is called echo. So I'm going to echo and then whatever string I put here. So I'm going to force everybody to say, I love this workshop, all right? And then it says, okay, so now standard out is captured by this notebook and it's printed here, all right? So there's a reflection of the standard out. So it's the same thing when we were doing the LS earlier. It came out to standard out and then it was captured by the notebook and then displayed here, all right? Okay. Okay, here we are. So there's no standard error, so nothing was impacted. So now I want to illustrate the thing that you can actually do something to this standard out, okay? So we can do 2 things. We can save the output because sometimes we have a large output. There's no point reading it. You just want to save it, all right? The other one illustration is that you pass it to a different program. So let's illustrate number 1 first. You redirect it to another file. So in this case here, you echo it and you just put a greater than sign. So if I echo this one and then, okay, just see, so my file is there. And then we can take a look of it, the contents, because it's a text, we can use the command cat to see what's the text inside, all right? So if I cat and then my file text, you can see that indeed, whatever standard out here was actually redirected and saved inside this file. All right, so this is useful. Later we'll see this symbol in one of the analysis that we're doing. All right, so number 2 is actually the thing where I talked about where you can pass it to a different program. All right, so we call it piping. So to do that, let's think of what program we can pass it to. So it turns out there's a useful built-in command called WC to count the number of characters or lines or words like that. So we can use the command WC. I put -c is because I want to count the number of characters. If it's -n, it's actually the number of lines. So here I'm going to say WC -c, and then after that, how many characters there in the file. Okay, so you can see it says here, okay, there are 21 characters here. All right, now instead of saving it to a file or anything like that, you can actually chain two commands together. So illustration on this, remember we initially did echo this thing and then we saved it into my file. And then after that, then only we ran it WC, but I can do it all in one shot. So we echo this thing and then the standard output is passed to the standard input of WC, all right? And then it comes out to standard out. So you get 21 directly. Okay, so it's an illustration in case you see the symbols later as we go through the example. Okay, so this one, just to let you know that sometimes there's confusion when we install programs. I install and then after that the program doesn't execute. And this one, when I was starting learning out this thing, this one caused no end of confusion for me. Okay, so a good thing about it is that we ran commands like WC and echo. We just type it and then it just works. But sometimes you may have installed something and then or followed some instructions, or someone told you, yeah, just use this command, and it doesn't work, and we don't know why it doesn't work. All right, so we need to find out where the programs are, because when you type a command to Linux, it will just hunt for it first in what we call a path that we'll see later. All right. So where's the echo program? So you can just use the command which. So I put down there and it says, okay, it is actually in /bin/echo. That's where it lives. Where does WC reside? Is in the different directory, usr bin, and then ends up in WC. All right. Now, how does it know how to use this one? So it turns out that Linux refers to this variable called path to tell it where to look for things. So we can have a look at it by actually looking at the path variable. So if there is a variable, we need to look inside. We have to put a $sign in front of it. So in this case here is echo $path, and then let's run it. Okay, and then you can see that there's a whole list of characters here. So this is one directory to look for, then followed by a colon, and then the next and the next. So you can see that echo ran because it was inside this path, all right? And USR local bin is also somewhere here, all right? So it actually knows where things are, all right? So that's how it finds the thing. Now you notice this word conda here. So a lot of the programs here were installed using conda, which is a nice package management system that allows us to install a lot of programs easily. All right. Okay, so let's have a look. Okay, so let's say so there is a small program here called welcome. Okay, so let's try running it. Okay, I'm inside this directory. So I should just type the thing and it should run, right? So I just run it and then it says command not found. So as I said before, when I started learning this thing, this one caused me a lot of confusion. So it turns out that it cannot find because Linux will go look into the path variable first and then search for it. So we are in a different directory here, okay, which is /home/BWF. So it is not going to find it. So the only way to specify that you want to run in the current directory is actually put a full stop and then a slash. So 2 dots means go backwards. 1 dot means the current directory. So // and then the name of the program. Let's see whether it works. Okay, good. So our small program says welcome to the workshop. Okay. So illustration we're going to shortly soon. It's like BWA. Then I can type it and then okay, BWA is working. So usually programs, if you just run it without any, you didn't specify what we call arguments or what you want it to do, what file you want it to act on. Usually by default, they will print out a list of things that you can do, right? That's a helpful function, but not all programs are like this. Some programs you need to specify -h for help or minus help or something like that. All right. So in this case here, BWA is fine. It just gives you output, so we know it's running. Okay, so apply the same principles to see, how come it's running. How is it possible that Linux knows where to find this program? Okay, so you can use which WA. Okay, is living in opt conda bin. All right, so just confirm That's why I told you, if you look at the path, you should be able to find it there. All right, it's the first thing down there. So that's why you can find BWA down there. All right, can. All right, so that's a quick introduction. Okay, so the other thing about this notebook is you want to accidentally created a cell. I can just put this one to just delete it. Now, if you're happy with this, you want to put some notes down there, it's fine. So what you do with this one? You can actually keep a record of this by doing this, all right? So you can go to up here, File, Export as, and then HTML. Okay, you can export as other things, but it doesn't really work as well. So I suggest you export as HTML. So it will be downloaded to your download directory. So over here, if I click on this thing that was downloaded, and now you have a HTML copy of it. You cannot execute it. It's not executable. It's just that it has just made a record of the thing. So next time, if you had, you know, run a list of commands and annotation, you can actually keep a record of it. So as an aside, later when we go through analysis, I advocate, if possible, we use such notebook systems to keep track of what we do. Because oftentimes, there's no annotation, and then somebody runs something, and then we have no idea, you know, what the sequence of commands was or why the person actually did it. All right, let's see any questions here. It's activated. I don't see anything. Okay, cool. Okay, before I move on, next one, is there anything on the chat? I'm not monitoring it. No. Okay. Okay, let me close this, and then we will, where do we do? So right now, you go have a look here. Remember, this is a depiction of the folder. We go back to the top folder, which is BWF2020. Okay, so I just click here. That will bring me up to the first one. So we have completed the first part as a general introduction or warm up, all right? And that took half an hour because it said 26 minutes ago, this thing occurred. All right, so I quickly click into this, and we'll quickly go through this. All right, after I just take a short break now and just have a look whether anybody has any questions. So I'm looking at the chat. Nothing? Okay, so I guess some of you are familiar with it. So I think this one was a revision, or maybe hopefully you had your cup of coffee or tea. All right. All right, excellent. Let's see, I'm mindful of the time because it's a Saturday. Let me have a look. Okay, so it's 10:30, we should be okay. All right. Okay, okay, maybe I should have just put a poll down there. Is it okay to continue or not? All right, can. So we will take it slow. So I just pause here first to make sure that everybody is on this directory. Okay, it should be BWF20 and then the second folder that we actually are going to go into this disease annotation thing. Oh, all right, cool. All right, so I've broken it into 4 parts so that we'll take it slow and easy, especially for those of you who may not be so familiar with it. So I'll try and explain some of the concepts there, all right? Okay, so I click on the first notebook and we'll open this. Okay, so I'll just minimize this. Okay, so the point here of this one is see how healthcare now is increasingly in need of bioinformatics expertise because those of you have read about the emergence of this field called precision medicine. I think the dream is actually using all these new technologies. Okay, it could be DNA, it could be protein or RNA, where the traditional test done in the clinic is actually just a blood test, and then we look for things like antibodies, look for things like the composition of like the ions and stuff like that. So you want to know your sodium level, your potassium level and things like that, all right? Or other molecules such as urea or creatinine, or things like cholesterol. All right, but right now, because of the drop in sequencing costs, and now people have realized that we can actually get more data. So the typical thing is we have your normal healthcare data. So it's like, you know, how old you are, and whether you're male or female, your weight, and other things like that. And there's also where we have the bioinformatics component. All right, so bioinformatics component, for example, next generation sequencing data and things like that. The idea is that these two things are better together. The knowledge of any variants in a patient may actually give some indication of what the disease process is. So we're going to use this example. So this one was a paper published, I think, in 2010. All right, in the New England Journal of Medicine, because it was the first, high-profile demonstrations that there is some value in actually sequencing when you're not sure what's going on. So, for example, normal diseases may not fall into neat categories. There may be some diseases that may be a bit, we don't know what's actually going on. Sometimes the clues can come from the genetic variants. Okay, so this is Dr. James Lupski. All right, you can go to Wikipedia page to read up more about him. So he sequenced himself and a few of his family members to identify some condition that the family seems to be suffering from. Right? So we're going to use workflow here. Okay, of course, not the same as what Dr. Lupski used 10 years ago. Okay, so this workshop here, we're going to talk about a reference genome. And then this is the actual sequence data, all right? So right now, what people do is that if there's a patient here or yourself, pay some money and then you give your blood sample, or depends on which area do you want to sequence from, but generally blood is a typical one. And then once you sequence it, then you end up with a FASTQ file, which I'll describe shortly. All right. So this FASTQ file here, basically, is just like raw data. All right. You need to get some, as Dr. Yam said, we need to get some insights into it, some information about it. Having just a dump of ATCG DNA sequences is not very helpful. So we describe a process where you need to check the quality of what you got out first before you process it. And then after that, we need something called reference genome. So the Human Genome Project was a massive effort at humanity to read its own book of life. All right, so that one was completed in 10 years. It took a long time, but now with sequencing technology, you can sequence the entire human genome in a day. So is this reduction in scale from 10 years, now we can do it in a single day, has now made it possible that it can actually enter our daily life. So I won't go through the specifics here, but just to tell you, we'll see this roadmap as we go along. That we need to do things such as alignment, and then after that you get out different file formats. We need to do some pre-processing, and then after that, this is the main thing where we compare the actual sequence that you got from the patient with a reference genome, all right? And then you end up with the variants. And then this is where the insights come in, where we have to try and interpret it, okay, as best we can. So we're going to use an example. It's a very clear-cut example. However, as many of you who may be working in research in bioinformatics, this interpretation part is very difficult. So it's something that's holding back our wide adoption of this type of testing. Because if you sequence, you tell a patient, okay, you're going to spend $1,000 on this one, and then the results come back in some form that you have no idea what to tell back. So that's not really value for money, all right? Okay, so for this tutorial, I took some time to squeeze everything down so you can run it on your laptop or desktop. Okay, I tested it on my 6-year-old laptop. It does work. For those of you not installed Docker yet, maybe after this session is over, those of you are interested, have not tried it, we'll see whether we can help you along. Okay, I think we want two things from this bioinformatics workshop, the beginning of it. So one of it is community. So the fact that now, I know people coming from Malaysia, particularly Johor, okay, single them out. And then people from Philippines, Indonesia, I think is great. So one of it is community, and we want to sort of democratize it. So if we can get something that runs on your local machine so that you can play around, then hopefully the learning process will be better. And this combination, this notebook will allow you to read the notes and execute as it goes along. And then you can add your own notes down there, all right? So this is just a taster of this thing. If there's a demand for it, we can actually have a different workshop to actually go through the notebook and how to use it properly. Okay, so without that, let's start with looking at the contents of the directory. Actually, you can see it here, but it's nice to see the details of it. All right, so let's do this and let's have a look here. Okay, so you have your notebooks here. Okay, so now we have two files here. This is the reference genome. Now we kind of you know, had to kind of cheat here because the entire file actually is quite big. Okay, we're talking about gigabyte of data. All right, but so here we just took only one of the chromosomes that we know is relevant to this analysis. All right, so you can see this one is a bit smaller, but it's still not exactly small. It's 177 megabytes. All right, okay. So when you guys were, those of you who try to pull down the Git clone, the lesson, it may have taken a while because it was trying to pull down 107 megabytes worth. All right. Now, important thing is that this other file, which came from the patient, in this case here was Dr. Lapsky. All right. Okay. Okay. So these are the two files. Now, the full data set, if you Google, you can go to this SRA database and then put in this ID number. You can download the full data set. I did download it and it was 4 gigabyte compressed. All right, if I decompressed it, it would be very big and there's no way we can run a workshop like that. All right, so for that purpose, it was downsized. Okay, let's take a look at this thing. Now we're going to use a command called head. Head means look at the first few lines, all right? Because I don't know, if I put cat, it will just list the entire thing and then the computer will hang because it will try and list everything. So use head here just to see what the first few. Okay, so this is the so the reference file is in a FASTA format, which is different from a FASTQ format. All right, we'll see later what the difference is. This format is the simplest format I've ever seen. All right, so basically the first line is the identifier. You just put a greater than sign, then after that you put some text describing something, describing things here. All right. Then after that is followed by the DNA sequence, which is A, T, C, G, and then N for unknown. Okay, because so if you look here, this is a sequence of chromosome 5 from beginning to end, and we started from here. So a lot of the sequences at the end cannot be sequenced. All right, they remain unknown. So that's why it's listed as N here. Okay. Okay, so let's look deeper. So I'm going to use a command just to jump ahead to see what's inside. So I'm going to use a combination of two commands. So if there's a head, there's a tail. Okay, tail means if that's a file, head means I see the top part, tail means I see the bottom part, all right? But I'm going to do something different because I want to see the middle. So I was thinking, okay, why don't we use combine two commands? And I told you about the pipe operator, so that I can see what's inside. So what happens is that any of these commands have a thing. So I can, so I have this thing here that I can say start from line number 10,000. So it's 100,000. So I do plus 1000. So if I put here tail, you must specify tail minus n. So that tells you how many lines you want to see. But I specify plus 100,000 means that it will jump ahead to the 100,000 line, okay, and then show me what's below here. But that's still a lot. There is a lot of things. Okay, let me redraw this one. Okay, so the command is I'm going to start at plus 1000, but it's going to list everything. So I don't want that. After I have this list, I pipe it to head. Head means show me only the top part. So I'm going to say show me only the 10 lines here. So I just combine both commands, okay? Starting from there, list everything, but then after that, show me only the top 10 lines, all right? So this is an example of where if there's not one command that will solve it, you try and combine two smaller commands, all right? So let me have a look here. So in the middle, you can see Okay, don't worry about this error here because that's a consequence of running this command inside a Jupyter notebook. Okay, there are some issues there, but it doesn't interfere with our workflow. All right. So here we can see that indeed, so this is a slice of the DNA sequence from chromosome 5. Okay, so because if I just showed you this, you will assume that, okay, this is all garbage, all right? But if I skip ahead, you can see that, okay, indeed, we have chromosome 5 data here. Okay, so that is the reference genome. That's what we want to compare it to. And the version that we're using is something called GRCH38. All right, so there's a huge consortium that actually updates all these humans. You may think that after the Human Genome Project that everything was fine. That was what we call a draft, okay? Just like writing a report or manuscript, that was the first version. Then as sequencing improved, no sequence is perfect. So what happens is that, let's say there's a sequence, there's some patches here that are hard to sequence or you don't know what's going on. As technology improves, they find out, oh, okay, there are errors down there, they start filling in the gaps, they start filling in. Then new versions came out. So the previous version was released, I think, close to 10 years ago. It was version 37. Now, some of you who are familiar with this may actually know this as HG19. So there was some slight difference in nomenclature. But moving forward, the next version that was released, they just decided to call it, standardize the number to 38, because sometimes last time you actually have to refer it to either 37 or 19, which caused some confusion. So right now it's just harmonized to number 38, which is the latest version. Okay, so I didn't tell you I didn't write down the details on there, but this is from this version. And having the version number is very important because it is like you having a dictionary that's many years old, and then I have a different dictionary, or I want to look up a word from the new era. So for example, the dictionary, for example, age 19, maybe it's like, you know, old dictionary, then a new word came about and I want to look up the dictionary, then I cannot find it there, or, you know, I may get a wrong definition. So having the matching of the reference and later, as you can see, add an annotation like that is very important. So sometimes a notebook is useful because we can actually write down these notes so that everybody is clear what it is. Okay, let's have a look at the query sequence. So here it is input.fq for FASTQ. Now, this one also was trimmed down for the purpose of this workshop, but generally, if you send anything for sequencing, usually comes back as a paired end, meaning that DNA sequence is sequenced in a forward and reverse direction. So usually you have two files, all right, R1 or R2 like that. Okay, but in this case here, I'll just combine into both, into one, so that it's easier for us to have a look. So let's look at the first 4 lines. So it'll use the command head. The option is -n and then 4 for the first 4 lines. Okay, so if those of you have not seen it, so this is what it looks like. So there are 4 lines per sequence. Line 1 is just identify, usually starts with @ sign, and then you can put here. Sometimes you can see more information here, all right? Then the next line is actually the DNA sequence. All right, so you can see that's the DNA sequence, a short read from there. And then the third line, actually they repeat it and it starts with a plus sign. But the important thing is, and it's different from FASTA, is that there's quality information now. So look at this one. This one looks as though it's a bunch of meaningless characters. All right. Okay, so the way I read it is each alphabet here, the DNA sequence has a quality score mapped to it. But this one is not meant to be human readable, okay, just ASCII code converting it. So there is a quality score called a Fred score, and then it's added plus 33. Typically, there are different standards, but the one that is typically used is plus 33. And this one will encode it and then it will map it to this list of characters here. So this is low quality, this is high quality. So for example, let me take this base here, G, and the quality is I. So where are we? It's very good quality, blah, 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 blah. Okay, somewhere not too bad, it's pretty good. I mean, To get to this one is quite exceptional. All right, so getting around here is pretty good already. Now, if you get any funny symbols here, means the quality is really terrible. And where do you see it here? Could this possibly be seen anywhere here? I think this is pretty good quality sequencing, but later we'll have a look at the quality using a graphical method. All right. Okay. So yeah, there's also a Wikipedia link where you can read more about it. Okay, so next thing is that let's see whether it's worthwhile processing it. So there are many ways of actually checking quality. The simplest way is just to graph the quality score along the read. So for example, this is a DNA sequence. We can graph the DNA sequence, and then this is the score. So the score will tell you how the quality varies as we go for DNA from 5' to the 3' position. Okay, so we'll use this program called FastQC because it has nice graphical output. So we'll run it. So all we do is just specify the name of the input file. Okay, let's run this, and then okay, because if we have trimmed it down, that's why it runs fast. Now, unless it's complete, we wait a few seconds here. All right, we should be able to see a new file down there. So we've generated a new file. You can see it here. HTML as well, you see it here. So over here, I can click on this, just treat it like a file browser. I click on it here, so now it's now we have the basic statistics. So okay, so we have 3,000 over sequences. You know, it's 91 bases, and then we scroll down. This is the thing that's what we are looking for. This is the quality of the read. So let me just stretch it a bit. So you can see that. If you look here, so this is it's from 5' to 3' direction. It ends at 91 bases. Now with new sequencing technology, it goes up to 300 or even more. And then now with long read sequencing, so these are all typically short read sequencing. New technologies such as nanopore can go up much higher. So you can see here that in the green here is generally what we call the good zone. All right. So we can see that base sequence is very good. And then after that, it starts dropping off. So this one is a normal characteristic of sequencing. I won't have time to describe it, but generally it's read base by base. As the cycle increases, that means you try and get the longer read length. The quality usually starts out quite well, and after that it goes downhill. So there may be some quality control that you need to chop off the bad sequences. But in this case here, they're all pretty good, so we just leave it alone. All right. Okay, so there are different patterns to this. Sometimes when a sequence read is bad, we can have very weird patterns like bad initially and then improve and then goes down, or some weird things like that. So having this general pattern where it starts out good and then slowly declines is generally hopefully what we expect. Then we know that it's usable. Now this one has got a lot more things down there that I won't really describe. So for example, this one tells you what's the average quality. All right, average quality per read. So it's like, pretty good. The average is, above 30. Generally, we just take it as above 30. It's like pretty good already. All right, a lot of these things are checking whether the bases, the composition, the GC content, all these things. Now, I just want to show you something here. So sometimes there are a lot of sequences that appear. So the FastQC actually analyzes whether there's overrepresented sequence. Now, when there's some sequence that appears a lot of the time, sometimes you think there's some sort of contamination. So FastQC does a lot of cool things, like you'll try and look whether there's what we call adapter sequences. All right, so for example, if the DNA sequence is read, what happens is that there's usually adapters at both ends. They're necessary because they need to anchor the DNA fragment so it can be sequenced properly. But usually after you sequence it, these will be removed. Okay, but if the removal is actually someone forgot to do it or there's some error, it's also good to see whether there's this artificial sequence. Remember, these adapters are not part of the human genome. Okay, they're just added down there so that it can help, so the sequencing is possible. So sometimes we just need to see whether there is what we call contamination from adapter sequences. So over here, they have the usual adapter sequences from the Illumina, as well as some other ones that are less familiar, and it will tell you that how many percentage. So basically, this is a very clean thing. We don't have adapter sequences, so we are not going to go through any what we call trimming. So if it's quite bad, we can do process. So for example, if this is an adapter here, we need to chop off that part. If the quality here is like quite bad, then we can trim off that part. All right. So basically, it's like taking a piece of meat and then you say, okay, this one extraneous fat, I don't want, trim it off. And then, oh, this part, the meat maybe looks a bit off, and then I cut off that part, leaving you with the actual meat of the thing. All right. So let me close this, and then we continue. Okay, so we are checking the quality. Sorry, let's move this, close it a bit. Okay, so so we have looked at that. So okay, we are good to go. Now we have to do some preparation. So recall that the principle of checking for variations is almost the same. So basically, you have a reference, then your input sequence, you just need to compare against it. So we need to prepare this reference genome. And the reference genome that we're going to check use is chromosome 5, okay, that we saw just now. If you had done the whole one, it's a bit too big and it won't, installing it will be a problem, okay, on a typical laptop. Desktop is fine, but laptop can struggle a bit. So we need to do something called indexing first to prepare this one, all right? And we are going to use the program called BWA, which is like the standard now that everybody uses. Okay, it uses a very cool algorithm called Burrows-Wheeler transform to compress all the information so it's easily searchable. All right, so it's very fast, can allow millions of sequences to be aligned, and you don't have to wait a month or two. All right, it can be done in quite quickly, an hour or so, depending on how fast your machine is. So let's run BWA to see what the options are. Okay, let's do this. Okay, so you can see there are a lot of options down there. All right, so the one that is the one that's relevant to us is the first one. We need to index sequences in a FASTA format. So we do have chromosome 5 in the FASTA format. So perfect. So we're going to index this one and then do it. So if you're using this one may take a while. So it'll give us some break, okay? So once you index, we should be good to go to the next one. Now, as I said before, we index only the chromosome 5 because we know that the disease variant is there. All right. The reason why is that indexing the full genome, about 4 GB, will take a few hours. Okay, so it will exceed the time that we have for the workshop, and most of the time we're just waiting around. Okay, so I'm going to run the command BWA index. Okay, let's go. So you can see that it's loading, and then this one will take a while. Okay, I think this one will generally take about 2 or 3 minutes. So it's basically packing the sequences. Okay, so compressing it in a form that it's easy. So it takes it goes through several iterations to try. So it went through 10 iterations. Generally, I think about 100 like that, it should be a bit completed. All right. So in the meantime here, while we're waiting around, let me have a look here. I hope this is activated. It says activated. Okay, no questions here. And I don't see any questions on the chat also. All right. So it's still going wrong. So do you want to see how hard it's working? Okay, we can go back to the terminal while this thing is running. Okay. And we do have a thing called a program called HTOP. Okay, just to see how things are running. So I'm running on my desktop now. I have 4 processors. It's running in a 4 GB container. For you, it may be 2 GB. It doesn't matter. It will still run. These are the list of programs that are currently running, and you can see that one of the cores here, because now a lot of processors are multi-core, is running at full speed. All right. Now, a lot of processors can be sped up if you split it among the different cores. But for this indexing process, I think no one has figured out a good way of actually spreading the work with 4 cores, because if you spread it, all the things will go out of order and you get garbage out of it. So for certain things, actually, it's very hard to what we call parallelize. Okay, so there's a lot of research work done on high performance computing that Prof. Tan Tin Wee will talk about after lunch. All right. That are crucial so that we can get our work done in a reasonable amount of time. So it's still running at 100%. And if you can see on the left-hand side here, there's some files starting to appear. So, okay, the index is getting built already. Okay, so, wow, it's still running. If you look, nobody can squint and see the top half of that. My fan is running at 97%. Okay, so if you're some of you are running your laptops, don't get worried if things start spinning up, all right? Because a lot of the bioinformatics work actually can be very intensive, all right? Okay, so you can see, all right, so what happens there is done the iterations. Now the next step is going to pack only the forward direction, okay? Then we should be done soon. So sometimes I just leave it here just to make sure that, so if you look here on the top thing, this is the process that's taking up the most time of the CPU. You can see the BWA index is still running. So that's thick and it's occupying 100% of that one core. All right, it's quite intensive. Okay, then suddenly I see, oh, now my fan is cooling down and you can see that all 4 cores are, generally back to idle already. So that tells me that it should be ready. So if I go back to the notebook, hooray, it's ready. So on my desktop, it took 192 seconds. Actually, I had no idea how. So if I don't know how many is that, so I can use this as a no, I can't use a calculator. So I can, let's see, so divided by 60, roughly about 3 or 4 minutes like that. So hopefully within 5 minutes, if you're running it on yourself, it should be. So I got a question that can BW run on multiple cores? Yes, the BWA searching runs on multiple cores beautifully. That's why it's such an awesome algorithm. The indexing is single core. Okay, and as far as I know, I haven't found a version that actually can index using multi-core. The good thing about building an index is just like you're just writing the dictionary once, then you're going to refer it to many times. So you suffer a long time once, then after that you reuse it multiple times. So this one usually is not an issue, and maybe that's the reason why people are not very keen on trying to find ways of optimizing it. All right, but any of you who are more familiar with algorithms like that, maybe you can enlighten me. There's a possibility of that. Yes, you can index on, I saw another question, can index on multiple chromosomes also. Yep, that's the way, if there's a natural thing. But generally, for efficiency of searching, we try not to split it up. So Prof. Tan will also talk some of this, maybe informally, about some of these concepts where you want to speed something up, you can do it what we call embarrassingly parallel. If everything can be split up into independent work, so for example, I'm going to get the students to do work, all right, and then I split up within 10 students to do all the work, and each student's work is independent of each other, then you can do it. You can just scale it up, all right? Okay, so let's have a look at this thing. So indeed, we do have all of these reference indexes already. You can see the size has increased a little bit from the original FASTA file. Okay, but it's a compressed form that's optimal for searching. All right, cool. So again, as I said before, once you complete one notebook, you want to add whatever you want, then you can export it out as HTML. In fact, maybe we can share all these things once it's all executed, so you can read it at your own leisure. So I saved it. Let me see. Okay, I must have hidden the window away. Okay, never mind. I'll do it later. So if you open that file, HTML file, it's just the entire thing, just so you cannot execute it. Okay, so now I'll close this. Okay, I just leave this one running so that we'll know. I flip back and forth just to see how my computer is doing. Then in some cases where it's running in parallel, you can actually see it. Okay, next is like, Okay, so we got the thing ready. So now we can align the sequence. So this one is ready. So hopefully we can align. But to do that, we may need to prepare the sequences. Okay, let's have a look whether we need to. Okay, sometimes, as I said before, we need to trim off and things like that. So in this case here, the quality was good. So let's have a look at the directory again. So just to make sure you got everything. We have the index file, we have the input file, we have the quality files. All right, so everything looks good. Let's look at the input file. So this is the input FASTQ file. All right, so just to remind you that every 4 lines is a different sequence. So we got about 3,000 plus like that. So scale down so that we can do it quickly. All right, so let's align using BWA. So let's run BWA because I cannot remember the actual command. So let's see. All right, you can see here that there are a few here options. So MEM is one algorithm. There's FastMap also. There's ALN and there's BWSW. All right, so there are many options here for alignment. And you can see the comment here. Basically, there are some for specialized applications. For our case, BWA MEM works for generally most things. All right, so we're going to use that. Okay, we'll follow the recommendation by the author. All right, so for those who are interested or more computer science, have a background, then you can read into why this is so, why this is optimal. Okay, so let's look at the options of BWA MEM command. So if you look here, actually there are many options here that we will just leave it as the default, all right? And that's why for those of you doing more specialized bioinformatics training, you'll get a sense why you may have to alter some of these parameters, particularly for some genomes that have problems with alignment, okay? So for this one, human one generally is okay. So notice here there's this command called -t. So this is number of threads. A thread is like a set of instructions that you can run in parallel. Okay, so if I specify 2 threads, then you'll try and run it on 2 cores, 3 and 4 and things like that. All right. So in this case here, if you go into HTOP here, you can see my desktop has got 4 cores. On your machine, if you run HTOP, you may see 2 cores or things like that. I think rarely we have a single core now. I think most things are at least 2. Some processors are 4 cores. So for example, Intel Core i5 or i7 is about 2 to 4 cores. Okay, unless you have a very high-end thing. All right. So we are kind of limited to how much we can make it faster here. But we are using only a small sample, so you don't see the speed up very much. So a simple alignment, we just specify 2 things. We just specify the reference and then the input file. In this case here, we can specify the -t option. So for example, if our FASTQ files were very big, then we will just put -t and put as big a number as your computer can tolerate. So you will split, you will just run the alignment on as many cores as possible. Okay, so in this case here, I don't think I can do it fast enough because the reason I wanted to run it here and then quickly switch here to show that it's running on all processors. But in this case here, I think it's a bit, let's try it out, okay? So how you run it is quite simple. You BWA MEM, and then after that, you specify how many cores you want to. If you forget to do this, and I've done this before, sometimes I forget to do this, then I get complaint. I say, why is this alignment going so slow? My machine has got 16 cores. Then I say, oh, okay, duh, I forgot to I forgot to put this parameter. The reason is, if you look at the instructions at the top, by default, it sets to 1. Now, this is it differs from program to program, okay? It's up to the author. So this author erred on the side of conservancy that if you don't specify, you just take out 1 core. Because some people who run it, some authors write applications that use up all the cores by default. And sometimes it's not what you want. You're doing something critical, you run, and then it just slows down the entire system, and then you're in trouble, all right? So it's how the author of the program chooses to set the default. So in this case here, if I run this, I specify first the reference file, and then after that, the input file. Now, ordinarily, if I just ran this, it will just spit out everything into standard out. So now we need to redirect it into a file. Okay, so we use the redirection operator or the greater than sign, and then we'll save it into a file called map.sam. We call it SAM because that's the alignment format name. Okay, let me try running this. Okay. Okay, you can see it's done. It's less than a second already. Okay, so there's no way I'm not that fast enough to switch back and forth here. Why is this? Because you've done a hard work of compressing the genome index already. So the algorithm is very fast, and we only got 3,700 reads. Just went down there and just align everything. So let me see whether it's faster if I just have one. It's still fast. So you can see that it took like 0.3 if I speed it to 4. Not much speed up. The reason is that you don't see the benefit until you have a bigger sample set. All right. Okay. Okay. Let's have a look at the output. Again, the head, and let's have a look. So you can see that, okay, the first few lines are just some description about the alignment. So it actually captures what command was used to align it. And let me see. So this is actually one line, but because there's word wrapping, so it ends here. Okay, so this is one. This is another one. Okay. So what you can see here, for example, is that is a tab delimited file. So this is the sequence identifier. Then after that, you have the chromosome, the position, how many matches, and so on and so forth. All right. And then they also have the actual sequence and the quality as well inside this file. Now, the SAM format, as you can read more about the description, but I just highlight a few things to you. So for example, here, each tab, the first field is the name, then there are other things as the position, the quality, and other things like that. So I won't go through everything, but I just want to give you an example here. Now, there are 11 fields that are mandatory. Then after that, people can add on different information. So for example, this alignment here, all right? So the first field would be, oops, sorry. The first field here would be the identifier. And then after that, the flag. So this one, we didn't have a flag. It will tell you whether it's a single end, paired end. There's a code for it. Then the reference sequence, the position. Then after that, there's a mapping quality, followed by this summary of the match. Okay, so this thing is called cigar. And don't know why they call it cigar, but I'll just show you how it's roughly read. Then after that, you have a lot more details about that. All right. So let's have a look at ours, the first 3 lines, for example. Okay, so in this case here, the first field here is the identifier. There's no flag here. The name is 154. Sorry, name is, so reference is actually chromosome 5. This read here that you see here is mapped to this position on chromosome 5. Okay, yeah. And after that, the mapping quality, which is 60, which is pretty good. And why is pretty good? The cigar here is 91M. That means 91, this sequence is 91 reads, 91 bases. So M means match. So 91 of them match. Now, sometimes you have things such as 1S90M or something like that. It means there's one substitution in front and the rest of it match perfectly. All right. So I won't go to the details, but this one is you at a glance you can roughly see where it's mapped to, what the quality is, and roughly everything match, or there's some issues down there. All right. Okay, so I won't go through the rest of it because that's a lot of information that is good when you're taking a deeper course on this one. But I hope the point of this workshop is to give you introductory intuition of what things are. Okay, everything else you can export this thing again. But in this case, I won't, so I will just stop it and then I'll open the next one. All right, so we're getting closer and closer to what we want to do. All right, I just want to go through this process first and explain, but I think the fun part will be the annotation part, because when you align it from a raw sequence, you see the alignment is like quite fun, because you can see, oh, this was some, you know, a list of like characters. I don't know what it is. Now it has got meaning on it. The meaning is that, oh, it's in chromosome 5 somewhere, but we need to extract more meaning to it, okay? And whether it does anything to a gene or anything like that. Okay, so now we are going down this workflow, and we ended up with this file called SAM, but we need to do something such as compress it to a binary format. As you know, text formats are not exactly the most efficient way of storing things, so it's converted and compressed to a binary format. Then we need to do a few things such as sorting the things, and if there are any duplicates. Now, one of the reasons why there's duplicates is actually in a lot of short read sequencing. So let's say the DNA sample, you shred it into pieces, but each piece needs to be amplified, okay, so that you can sequence the thing. So during the amplification process, you will have a lot of duplicates that will actually cause some problems in the variant calling. Okay, it may just give a wrong representation of the amount of variants down there. Okay, so this is the preparation and things that we need to do. Okay. Hang on, huh? Let me have a look. All right. So before we go into this one, maybe we take a break now. Because I realize I still need to drink at that, and we need to all move our bodies and keep safe. So why don't we come back here at 11:30 if that's okay? All right. So I leave this thing here so that we have a preview. So we did some of the preparatory work already. Then we'll follow the preparation and then the variant calling. All right. Let me see. Let me erase this, and I will see. Okay. I have a question here. Every time you restart Docker, all the files are lost. How do you prevent that? Okay, this one is, there are many ways. Okay, so all of you got a break, but I'll just answer this question here. Okay, thank you for the question. So now this one is an issue, and this is what we call persistence. Okay, if you're not familiar with Docker, maybe this is not the time to do it, but let's see. So if you can see my screen here, make it a bit bigger, clear things. So Docker, yes. So let's say you have stuff down there already. Okay. Now the thing is that you can actually save a new image down there, and you have to do a Docker commit. I won't do it here yet. So you need to do things such as you need to stop the container. So there's a difference between stopping, and then after that, after you stop already, I can say then Docker remove. If you do that, everything is lost. Now, if you do Docker stop, it just stops the process. It's still on your computer, the files are still there. You can restart it. But what you can do is actually after that, do a Docker commit. And then you'll write a new image and freeze whatever you have done. Then you can continue another day. Okay. Then let's say, okay, why should I try doing this now? Okay, it's a bit dicey. Let me see whether it works or not. Okay. Okay. So if you're not sure what this is, you can look at the documentation for Docker commit. All right. So let me look at an example. Okay, let me try doing this. Okay, I'm going to stop the container first. Okay, I hope nothing happens to it. So how I can look at identifier, the identifier is the container ID here. So it's a long string, I can copy and paste, but actually you can just take the first few characters. So 8F is enough already, it's unique enough. So I'm going to stop it. Okay, it takes a while to shut down the processes. And later I see whether I can restart, otherwise we're going to have a problem. All right, but we're coming back here at 11:30, so I can. So now if I have a look at Docker again, it's stop. All right, then I can do Docker commit. All right, meaning that I want to save this image here. And here is, okay, so we can, so what we do here is, okay, so I'm going to commit which one. So I'm going to commit this container. So let me just, for be sure, I just commit this container, and then I don't know, what do I want to call it? My BWF, and then I can put a colon as a tag. Maybe this is version 1 or something like that. All right, so if you do that, it takes a while, so I hope you have hard disk space, all right, because it writes a different file. Then after that, you want to see where it is, you just put Docker images. Okay, so I have quite a few here, so it's hard to see. But if you look at this here, this was the initial one that you got originally. Now you have my own one, okay? So this is on your thing, created just a few seconds ago. And it's increased in size because we did some processing and stuff like that. All right, so next time you want to run it, instead of using my name, then we just continue this one. Let me see whether it works or not. Okay, let's try. So let's say I want to continue from there. Docker run -d. Now instead of saying that one is that my, so I'm going to expose the same thing port. Okay, but now I just put my BWF. So it's on my machine. It's not the one that you got down. Let's see whether it works. Okay, now it runs, but now did it continue? Okay. Okay, let's try. Okay, let me refresh the thing and see whether I screwed things up. Oh, okay. Okay. Is it running? Let me try. Oh, okay, it's running. Okay, it works. All right, hopefully that answers your question that you want to freeze, you have done some work already, you just want to freeze it, you stop the Docker container, then you commit to it, and then you give it a new name that makes sense to you, all right? This is not a Docker workshop, but you can read more about Docker commit, all right? But I hope I give you an illustration. Okay, so I'll take a break, I will stop the video. Okay, I stopped talking, I've been talking too much. Hopefully you're not asleep. And then we'll continue, all right? 11:30, see you guys back. All right, welcome back. Okay, so I have this habit of you know, when I'm on a roll explaining something, I just go and on. So feel free to pick and say that okay, we need a break or something. But I think it's a good way to pause, because after this we'll just finish off with the variant calling, and then we'll spend more time annotation. All right, and hopefully we'll leave some time for questions. I hope this will be, because the introductory one is just to get to know each other and see one of the ways of actually we can teach bioinformatics in this new normal environment. Okay. All right, so I don't see anyone in the chat. Just a reminder that you're welcome to post questions. There's somebody who posed question already on poll EV. All right, BWF 2020. All right, so everything is okay. I don't see any other questions. Neither on the chat. I think we are good to go. All right, so now let's review where we are, or where we left off. All right. So recall that we have the input sequence. We had the look at the quality. All right, it looked good. Then after that, we created a genome index with all these indices here. Then we combined the FASTQ together with the index, and that generated the alignment file. Okay, the SAM file. And we took a look at the SAM file, and the critical things that we saw was that it could actually map it, some of the reads to chromosome 5 at a certain position. There's an indication of the mapping quality. All right, that tells you that whether how confident you are. And then there's also something called CIGAR, which actually gives you a very compressed way of describing whether, you know, which parts of the sequence match the reference. All right. So I said before, now we're in the next step where we want to do variant calling, but we need to get it in a form that the variant caller can accept. And this is what we'll talk about now, right? From the aligner, which was BWA, we are now at the SAM format, but we need to do a few things such as compressing it. Then after that, sorting it, indexing, actually marking the duplicates. I described just now that because a lot of the sequencing requires PCR amplification, sometimes you can introduce a lot of duplications that can bias your variant calling. So these need to be removed, or at least marked in the sequences. All right, and then after that, we'll finish off by actually the more interesting part, which is actually trying to see whether we can re-identify the disease that Dr. Lupsky was suffering from. Okay, so in order to do that, we prepare them by compressing it. We need to sort it, mark the duplicates, index it, index stuff, and then after that, we're good to go. All right, so firstly, recall that we generated the SAM file. And we need to process the SAM file using a package of tools called SAM tools. All right, so we take a look at this thing called SAM tools, and I use a command called view that we can see what the options are. SAM tools does a lot of things, but we're just restricting it to SAM tools view. So you can see here that things of interest to us are, you can output a BAM file. In fact, that's what we want. Nowadays, there's an even better compression called CRAM file. But I think for the purposes of the workshop introductory, we just concentrate on the BAM files. Okay, any other option that we... was I muted? Okay, then I better... sorry, did I unmute just now? Okay, so if I did you didn't hear me initially, then I'll just continue here. All right, so we'll talk about variant calling, and we just recap that we, yay, finally, sorry, nobody, okay, I just realized that I was muted. All right, so here, recall that we generated the index, we had a FASTQ file, the quality control, and then we ended up with the SAM file. All right, and we needed to prepare a few things, and this is what we'll talk about initially. Yeah, all right. And I mentioned before that we need to do a few things. We need to compress it, sort it, make sure you remove the duplicates that could bias your variant calling, and then we do some more indexing. And these are preparations needed so that the variant caller can take place. So to compress the SAM file, we use a tool called SAMtools, and we'll use the SAMtools view function over here. So let's have a look how you run it. So SAMtools view, you can put the input file, and then after that you can output the BAM file. So what is needed? Okay, we obviously need the output BAM file option. All right, let's have a look. There are a lot of options here, and also we require to specify, I think, the reference file. Okay, so how do we do this? We put SAMtools view. Remember, we wanted output BAM file, and then we also needed to specify a reference file. So the reference file is the chromosome 5, and then the file that we want to convert is the SAM file. And then if I run this alone, it will just come out to standard out. Okay, so standard out, and basically here's standard out. You can redirect it and save it to the BAM format. All right, so let's run this. Oh, thanks. I was only muted for 2 seconds. Okay, thankfully I didn't had a sense of deja vu or Groundhog Day that I repeated in greater detail the next time round. Okay. All right, so let's have a look. We should have a BAM file here. Okay, great. So there is a BAM file here. And notice that it's compressed. So initially it was about 963 kilobytes, and then now it's 200 over. All right, so this is useful when you're doing a lot of work. Okay, it needs to be compressed down. The next thing is that we need to sort it, because the variant caller expects all the alignments to go from, for example, chromosome position from the smallest to the largest. So it's easy for it to look for variants, because if it's all scattered around the place, it's hard for the variant caller to look for sections where there could be variations. So to do that, we use SAMtools sort. Use the option O to say that we want to generate a sorted BAM file. So you can name it whatever you want, but by convention, sometimes I like to put, like, if I start with map.bam, then I just put whatever manipulation as part of the file name. So it becomes mapped, and I know I sorted it, so I put .sort and then it's .bam. All right, you can choose whatever file name you want. As an exercise, we'll go later after the workshop, you can play around with it and try and put your own names and stuff like that and redo the analysis. All right. The next thing is that after you create the sort file, you need to index it. So we do SAMtools index. All right, let's run this. Okay, you don't really see much. Actually, let's have a look first. Okay, let's confirm. I create another thing and I put ls minus lh just to see how big it is. All right, so now we have the sorted file. So it's just sorting it. We're not changing the size of the thing, all right? And then there's an index file that goes together with it. Now the index file is important for a reason. There's a peculiarity of when you compress something. So let's say you have a text file. Text file, very easy. There's a line number, right? No problem. So I can say I want to skip to that line number. But when you compress everything already, it's a bit hard to find where ticks are. So so what people do is that they generate an index here, so that when you want to find something, it has an index here that can refer and skip to the part it wants. Otherwise, it will be like reading. For example, you want to check a dictionary, okay, A to Z. And if you don't have an index to go to the actual place, you have to start from A and then look. And then it's worse than trying to look up something that's in Z or Z. You have to go through the entire thing. So that's why there's this need that we typically have to index stuff so that the computer can look for it. This is what we call random access. All right. Okay, the next thing, as I mentioned before, a lot of PCR processors cause a lot of amplification of reads beyond beyond which it can cause a lot of bias, so we can actually mark the duplications. So here we're going to use another different program. SAMtools, it doesn't have that function. So somebody wrote another set of SAMtools called SAMBamba. All right. I don't know why the person named it this way, but it's quite cute. And it has another function called mark duplication. So it's how you do this is that you say the input, what you want, and what you want now. So I made this part a bit compressed, but let's say we want to see what it is. Oops, sorry. The other thing is so you can move the cells about. So I can just change it here, lower down here. So let's have a look at Sambamba. Oops. By itself, okay. So it says here that, okay, it's got all the other functions, or the mark duplicate is here. So maybe I run it as mark dup, and let's see any help given to us. Okay. So unless I'm not sure I'm running, and then I can either read the documentation, or I run it and then the help file comes out. So it says you put the input file and the output file. That's all. And for large ones, you can actually specify to parallelize it. Okay, or you want to do you want to compress it further and things like that. So there are many options here, but for purposes here, we don't really need anything fancy. All right, since our data set is reduced. So let's run this. So it says here that, okay, I ran all these things and I found quite a bit of duplicates. All right. Okay. Okay. So let's have a look what the output is. And yes, so I created a file. So I use the same convention. You don't have to follow this. This one is just by convention. But the drawback of this method is that it becomes sometimes if you do too many operations, it becomes very confusing. So basically, if I read it from left to right, first it was mapped, then it was sorted, then after that it was deduplicated. All right. So it helps me keep track in my mind when I read the thing, like I have no idea what happened. All right. So this we have deduplicated, and also we have the index there as well. Okay, cool. Now, I told you we have also, because to make it easy to search, all right, it's good to index stuff. So we have already indexed the input map files already. So now we have to index the reference file. So when a variant caller looks at it, it can actually search for the right regions quickly rather than going through serially. All right. So we use SAM tools here to index the reference file. Okay. In this case here, we're using chromosome 5. Okay. So run it. It should take a while. Okay. Great. Then after that, we have a look here. And where is it? Okay. So it's called .fai here. All right, so it's indexed here already. Okay, let's have a look inside. So this one tells you that there are some indexes here that help the computer find where things are. All right. Okay, cool. Now the meat of the thing, which actually, you know, after all that taster like that, is actually get to the real thing, which is actually variant calling. All right. So here we're going to use a very commonly used program called Freebase. Now the gold standard is still this thing called GATK by the Broad Institute at MIT. However, it's a bit more complicated to run, and I found that if I run it in a small container in a laptop, it tends to crash. So for purposes of this one, I chose something was simpler to run. Okay, so Freebase is still very widely used. It's very accurate. Okay, and it's known as a haplotype-based variant caller. Okay, I won't go through the details here. I think you can Google and find out a bit more about explanation. Now, typically, the simple way of doing things are actually, let's say there's a read, then you just align all the reads. So you see something that is always in that position, and voila, you call that a variant. Okay, but in actual cases, it's not that simple because you have one read here and it's aligned. Sometimes alignment is off a little bit by one. So like this, and then suddenly off by one, off by one. They're all the same mutations. But sometimes the sequencing may have, you know, what we call a deletion. You miss something and whatnot. So it's slightly shifted here and there. So in this case here, if we just use what we call precise alignment to call the variants, it's you're going to end up with missing a lot of things, or even calling some wrong variant. So in this case here, people have developed what we call haplotype. Haplotype is like a block like this that goes together. So you consider the variance as a whole region rather than looking at one thing, and it doesn't take into account whether things are shifted slightly. All right. So over here, let's say they're looking for this region, then they just look at the whole thing and count how many times haplotype there are any differences. Then they do some probability calculation based on Bayesian statistics to see which one is the most likely variant. Okay, so that's FreeBayes for you in a nutshell. Okay, so FreeBayes, let's have a look what the options are. Okay, so here you can click and read about the preprint. This curiously a case where they never actually submitted it for peer review publication because I think, I'm not sure whether they found it worthwhile or not, but it's been used multiple times since the archive was cited, right? Okay, so I won't go through all this one, but I just want to show you the example. So you can see that it is quite simple to run, all right? So I'll look at this one, which actually the simplest one. So this is a diploid sample. So we are all diploid organisms, all right? 2 copies like that. The number of ploidy or copies is important because when it does the probability calculation, when there are more copies of that, it actually influences whether something you call a variant or not, right? So so this is an important consideration. So this one is very simple. It's just FreeBayes minus F, which specifies the reference file, the BAM file that you have processed already, which is sorted, deduplicated, and then you output and then extended out, and then you redirect it to whatever file you want, and you call it a VCF file. Okay, this is a variant format. Okay, so we just use that option. You can see that this is a very versatile program, and you can do many things with it. All right, you can read more about it. You can see a lot of options here. Okay, this probably require another course to use it properly. So we use a simple one. We're going to generate a file called result.vcf, and we're going to use the redirection here. So minus F, we're going to specify chromosome 5 with the index as the reference, and then we're going to pass in the BAM file, the ones that's sorted and duplicated, and then we will save the results under result VCF. Okay, let's run this. This one will take a while. Let me have a look at my terminal. So if I want a terminal, I press a plus sign here. I say I want a terminal. Okay, and I type htop, and let's see how is it running in my container. Okay, it's running. And notice here it's running as a single thread. Okay, to run it in parallel, we need to split the file into different regions and then call the variants in different, then combine it together. But in this case here, I didn't bother doing it because our sample is pretty short. All right. So, as I'm talking, it's done already. So, yeah, you see the load has decreased. So let's go back here. So we see here it should be okay. So we can see the result.vcf file here. Okay, so let's talk a little bit more about this variant call format. Obviously, as with many formats, it can be quite complicated. This example here taken from I think Wikipedia. So here basically the format is you can see the chromosome, the position. If there's a known SNP means a common polymorphism because we are all different. So differences between what we call healthy or normal populations is known as a SNP. All right, a polymorphism. So sometimes these have been identified, so they can actually give it a tag down there. Then the next column is ref or the reference. What was the reference? And this is what was what did they find in your BAM file. And then the last one is here that I won't talk about the rest, but the one is quality. So generally, you know, above 30 or so, maybe then the quality is considered pretty good because otherwise the variant call may be a lot of errors and things like that. Even though they did call it, you may have to filter by quality to get rid of all the spurious variant calls. Okay, so the basic fields here, as I said before, the things that we want to look for are maybe up to here. All right, chromosome, position, whether there's a SNP identifier. Sometimes that, if you see it there, means, oh, the variant is known. Somebody has detected it previously. It's not really novel. Then the reference, and then what you found, the alleles that you found, and then the quality score. Okay, this will help you in actually reducing, because a lot of these variants, once you run the whole genome, you get a lot of it, and trying to get meaning out of it can be quite challenging. Okay, so I'm going to have a look at the first 100. Now you can see that this format, oops, sorry. So this format here, the first lines are all the description. So it just tells you that, if you see this one, the info, the tag like that, this is what it means. Okay, so it's like documenting what those different fields mean. These are in addition to the common fields that everybody uses. So Freebase has other things here that it includes as part of its processing. That may be useful for some people who want to do additional analysis. But you can see it has got a lot of output here, but let me scroll down to here. Okay, so you can see at this point here, it gives you the description of the header, the chromosome position, whether it's a SNP ID, the reference, alternate quality. So let me read this one here. Okay, so they found a variant at chromosome 5 in this position. There was no known SNP ID at this point. And then after that, sorry, the ID is this one because this one is slanted. And then after that, what was found in the reference genome and what it found in the BAM file. And then it tells you the quality. Okay, so this one doesn't look like good quality. All right, 0. So it means that maybe if I have a lot of variants to look at, I may have just had to filter this one off because I'm not sure whether it was a good call or not. All right. Okay, so we're done with that. You can do the same thing and export this file out for your reference. All right, now we're going to move to the last part. Okay, let me close this. All right, so we are at the last part here. So this whole workflow, we have a VCF file and we're going to annotate it. Now, annotation got many strategies, but we're going to use something very simple. We're just going to do cross-referencing. So there is an annotation database down there. People have actually pre-compiled. They've done all the hard work aggregating all the information of what variants that have potential functions. So we're just going to cross-reference it. Now, this one seems like a simple process, but if you have a lot of variants, it can take a while. So people have been working on ways to optimize it. All right. So we're going to use a suite of programs called SNPF and SNPSIFT. All right. It comes together. This is the website. You can click and find out about it. So the SNPSIFT2 is like almost like was sifting thing. So we're going to download a database and then we're going to compare what our VCF has to this variant database. Now, we can do a lot of fancy things, but unfortunately, I decided against it because one of the more fancy things, you can use SNPF and really annotate everything, the prediction and stuff like that. But a database, I tried it, it can go up to 15 gigabytes. Okay, so yeah, this is not something that we'll do for a workshop, at least. Okay. Okay, let's have a look at this thing called SNPSIFT. And let's run it. Okay, so blah, blah, blah by this author. And there's so many things here that you can do. You can filter, you can join things. Sometimes you got variant calls from different things. There's same population you want to join. You want to see what's the difference, what are common ones. There are many things you can do. But in this case here, we are just concerned with this one, which is annotate. All right, so there are many databases. So one of the big databases is DBSNP. But we'll do this because it's a very large database. So we're going to use a different database that is more for people who discover some mutations or variants that are important clinically. So in this case here, because it's healthcare, generally we can use this one to give an indication whether somebody else in the world has found a variant that has clinical consequence. All right. Now, how do we do this? Okay, so just a reminder what our files again. Okay, blah, blah, blah. Okay, so this we have all reduce all this thing to this one, the result VCF. Now we're going to there are many databases you can compare it with. So I think there's a big one called NSFP. This one is very large. It just basically amalgamated a lot of bioinformatics predictions, you know. So how they think, simplistically speaking, how you think that a mutation or variant may be problematic is that it causes a non-conservative change in, for example, the protein coding. Okay, so it's a conserved region and then you change it to amino acid that is really of a different physical chemical property, then the chances of it being causing a problem with protein is higher. Okay, so there are many different ways of actually, people are constantly finding new ways to try and infer whether a variant has got problems. Now later you can see that this one's a problem that is limiting our adoption in the clinic, all right? Okay, so we will go against the ClinVar database. So if I click here, you can read more about ClinVar, you know, in nucleic acids research, about how people have been submitting a lot of variations throughout the world and they catalog everything, all right? So it's almost like a gathering hive mind of all the work that's been done down there in the clinical space. All right. So as I said before, it aggregates data from various labs and expert panels. Okay, so now we have to download the correct version. So if I click on this, because there's a link down there that tells you which one. Now you have to pay attention because sometimes I've done this before. I chose the wrong version, and then when you annotate it, you end up with garbage. Okay, the reason is when you have a genome, remember I said that let's say this is version 37, 38. Sometimes they patch things because they found that there were gaps and then they patch things. Now, unfortunately, some of the patches cause the coordinate to shift in certain regions. So if you use the wrong version, the address will shift and then it becomes problematic. Then you may get an erroneous conclusion. All right. So in this case here, we chose 38. So make sure you click on the right link, but don't worry, you don't have to do this because it's inside the next. So right now we are going to download the 2 files required from NIH. So this is, I think this is the latest. It was released a few days ago. Okay, July 20th. All right, so let me run this and hopefully my internet is okay and we will get the files down. So now let it download, okay? So I decided to let it download live because it's not that big. All right, it's compressed and there are not many clinical variants out down there, okay, compared to all the bioinformatics predictions. Okay, so it downloaded both the files. Let's see, is it here? Yep, I can see it here. All right, so now we can use SNP-CIF to do a few things. So recall I talked about when we have a lot of variants, one of the things that we can simply filter is the quality, because if the variant caller actually, oh, it's probably just in and out, okay. So for a variant caller, sometimes there's a lot of errors in the base calls and things like this. They can actually lower the quality of the variant call. So I think it makes sense that sometimes as a first pass, we just remove the quality. So usually people typically take 30 as a cutoff, all right? So here we use SNP-CIF filter to filter. So I go SNP-CIF filter, and then there are many commands. You can actually filter by many things. I can filter, I say only one variance in this chromosome without a DB SNP with a certain quality. And the link, when you click on the SNP-CIF, you can read up more about it, all right? So basically, we're going to specify this filter here. I make it simple. The input file, which is the results, and then I will redirect the standard output to this file, the result filter.bcf. Okay, let's try this. Okay, so I didn't see anything here, but wait a few seconds, it should appear on the left-hand side. Or maybe not. Yes, it's here. Okay, so the result is there. Now we annotate it. So basically, there is a VCF file with all the different variants of people have studied it clinically. So it could be a variant that people have studied. They suspected it was a disease causing, then they found out it wasn't. They still annotate it and say this one is likely to be benign. In some cases, they've actually reported they saw the variant actually has got very good evidence that it is causing the disease, then it's called pathogenic. All right. So let's run this. Okay, this one runs pretty fast because it's a small thing, but you can imagine you have a whole list of, you sequence a few 10 people like this, and then you run it across. It can take some time. And Prof. Tan Tin Wee later will talk about you that a lot of these things are actually not scalable. Okay, if you just use a single machine that you buy in the lab, you need to aggregate and use principles of high performance computing to get things done. Because otherwise, you sequence something, you tell the patient, come back 6 months later. I don't think that is something that's scalable. All right, cool. So over here, you can read some statistics. Okay, so after filtering, we filtered down to 9 entries of good quality. And out of that, they found 8 results inside the clinical database. All right, so we'll look at that. Okay, let's have a look at the annotated file. Okay, so annotated file is here. And there are many things here, but I think the thing that we should just easily pay attention is, like, for example, clinical disease, CLN disease, okay? Now, allele frequency also is interesting because it allows you to try and make some inference about whether this is likely to be a disease. So for example, if you see some condition, a patient with an uncommon condition, you sequence it, but then the allele frequency means in the general population, how frequent is it? If you see it a lot, quite frequently, like say 0.5, that means half of people got it or something like that, then it doesn't quite make sense. You're seeing somebody with a rare condition that usually you don't see, and then when you sequence it, you find that that suspected variant has a very high allele frequency, so it doesn't match. So sometimes we can use these things to try and filter down again, to try and narrow down. Again, it depends on your use. So there are a lot of diseases actually are not caused by, are not rare, like high blood pressure and things like that. But high blood pressure is caused by multiple genes. So looking at 1 or 2 of them doesn't really make sense. So this is where another active area of research is, like trying to see how we can predict using multiple variants out there for a lot of what we call polygenic disease. So polygenic diseases are very common. Okay, heart disease, strokes, high blood pressure, cholesterol, like that. Okay, so it's a very active area of research. We don't have the answer yet. So I'll just say that we can look at the disease. You also see what is a predicted molecular consequence here. All right. Okay, let's have a look at a result. So I'm going to use the word cat just to list everything. All right. Okay, let's have a look at the thing, blah, blah, blah. Wow, there's a lot of description here. And then if you look here, the first one, okay, there's a better viewer for this. Right, but we'll just quickly look through here. So let's have a look at this one. So this first information just comes from a normal VCF file, no change. All right, chromosome, position, then after that, the alternate, and then the filter. So pretty high score. Our filter work, it's not less than 30. Then after that, it added a lot of information here. That's from the clinical database. Now look at this one. So this one says, this is the allele frequency. Okay, allele frequency from the different cohorts. So it's like 0.4, 0.3. Not sure whether this is likely to be a disease causing because it's pretty high. But it says that, oh, there is a clinical disease that is implicated in this gene. So this variant occurs in a gene that is known to cause a disease, okay, called Charcot-Marie-Tooth syndrome. All right. Now, after that, you can see some other information here. For example, this one is the review. It says, okay, multiple criteria provided. People looked at it, multiple people. That means not just one person. A few labs have also reported it, all right? And there's no conflict, meaning that nobody disagreed about this, all right? And the significance, clean significance, is benign. Okay, so everything makes sense so far, right? Okay, so we have this thing, very good quality control. Over here, it seems as the allele frequency is pretty high, and all the so far the reports come in is that it's not causing this disease. All right, so we can discard this as a possible cause of in this patient. Okay, Dr. Lupsky. Then that. So I won't go through so much yet, but I just want to tell you that the significance of a variant is classified into different tiers. So you can see these words as either pathogenic, then less likely is like likely pathogenic. Then in between is this thing called variant of unknown significance. So this one is a major problem. In fact, over 80 or 90% of variants that come out of a report are unknown significance. I have no idea what it is. You can use bioinformatics tools to try and predict based on the principles I talked about, but you don't know. And this one is a problem because there was I think there was a lawsuit last time where initially there was a variant of unknown significance, but you know, research continues, right? And turns out that this one later people classify as pathogenic, but the patient was not in, the patient already left already. So patient didn't know what's going on. Then later on developed the disease. Later she found out that it was called pathogenic. So there was a lawsuit going on and says that that doctor or that lab that initially said that it was unknown significance, you're responsible for missing this. All right, so you can see that the bioinformatics work, how we curate data, how we analyze like that actually has real world implications. All right, now I just want to show you this one. If I just scroll up a bit, you can notice that for some clinical significance, you can see the word pathogenic or likely pathogenic. So you want to narrow down this thing, I can just quickly just have a quick look at the possible pathogenic one. So we use a tool, grab. Grab is just search. So the way you do it is that you grab what you want to look for and then the name of the file. So I'm going to grab the word pathogenic in this one. Let's have a look how many there are that actually, because the rest of it may be benign or things like that, right? Let's see how many are we looking at. Oh, it looks as though we just narrowed down to 2. Okay, 2 is a good number to work with, all right? Then we can look at this more closely. So it is this location, this the variant as well as this one. Let's look at the quality score of the variant call. Very good. Okay, more than 30. So we're quite confident these are good calls. Next check is check whether there's any allele frequency down there. Okay, there is no allele. It's supposed to be somewhere here. There's no allele. Okay, here it is. The allele frequency here, AF 0.00088. So it's not a common allele, which makes it, so this is an uncommon disease, it's an uncommon allele, so it does make sense. I would say this is pretty high confidence, all right? And then this one, oh, there's no allele frequency here. That means it wasn't high enough to be detected. So this one also a very good candidate, all right? Okay, so we got 2 good candidates. Now let's visualize it. Okay, so now we're going to prepare it for visualization, and we're going to export and download the file out so that you can visualize it using IGV, which is a genome browser. Okay, so to do that, we have to do some processing. We first need to compress it. Okay, we use a program called bgzip, and we're going to compress it here. And remember, when you compress something to aid the computers finding out where things are quickly, you need to index it. So we use a program called Tabix to annotate it. To index it. So let's run this too. It's pretty fast because it's a small file, and then let's have a look where the file is. So we ended up with these 2 compressed files with the index. All right. So what do we want for visualization? We want the BAM file. Okay, because later I'll show you, it's quite useful because you can see the reads and then you want the annotation. Okay, so we'll download these files. So we're going to download these 4 files here. Okay, and then we're importing into IGV browser, and you should choose the GRCH38 genome, because otherwise you choose the 37, the coordinates all will be wrong. You end up looking at the wrong gene. Okay, so make sure when you have IGV, you choose the genome as HT38. It should appear here, all right? Then at the bottom here is actually the genes in the normal SG38. After that, you go to file and then load from file and then load these things in. Okay, let's do this. And let me see how to do. Oh yeah, I need to download the file first. So over here, how to download it? Let's say I want to download this file. Just right click, download. Okay, then unfortunately, Jupyter cannot download. I cannot multiple select and download all. You have to just download one by one. All right, then the annotate GZ file. Then the annotate TBI file. Okay, download. So let me see. Oh no. Let's have a look here. Yeah, okay, that's my download folder. So a download folder, I have the 4 files downloaded. Okay, so now I will start up IGV, which is here. Okay, so you should choose the human one and then go to file, and then I'm going to load from file. Okay, then I'm going to choose one by one. Okay, sorry. Let's see whether I can load everything together. Okay, sorry. Just load. Don't need to load the index. You'll load the index by itself. That's why it's causing some errors. Okay. So despite that, everything loaded already. So there will be 2 tracks. One is the VCF one, and the other one is the BAM file. So you can see the reads. Okay, we have no idea what's going on. All right. So maybe we go to chromosome 5 because I know that's where to look at. Now, IGV tries not to show anything until you zoom in further. All right, so we have to use this thing here to zoom in further. I need to zoom in further, but I don't know where to zoom in. So I can go look around. Or what's the better way? The better way is actually, okay, the 2 ways. One is that you can actually increase, it says here, it gave you a clue. You can't see anything. You can right click to increase feature visibility, because the reason why it's not showing everything, typically there are a lot of variants on that. So it cannot show a lot of things at once. It look very messy. But for us, we have narrowed down to only a few. So I can right click and then I can here set feature visibility window. And then it says here, if you want to load, show everything, put 0. 0. Okay, so 0, and then I zoom out. So if I zoom out, you can see, is there a mark here? Yes, there's a mark here. So the entire chromosome, so this on the Q arm of the chromosome, and you can see some variants down there when I zoom up. Okay, so I just click here and then keep on, zooming in further and further and further and further. Okay, so you notice something here that on this side, you can see that a lot of the variants here are actually around this gene already. Okay, so let's go in further and further and further. Oops. Okay, so it may be hitting. So the gene is actually from here. I think it's transcribed this direction. Okay, so most of the gene here, the coding sequence is on this side. Okay, let's have a look. Let's zoom in further. Now, if you zoom in far enough, then you can see this thing. So these are the actual reads from the thing that's all aligned and sorted. So let me just zoom in quickly. So I just want to show you how a variant is called. So you have a look here. So if you zoom in enough, you can see differences here. You can see there are a lot of, always there's error. Single isolated. Each one here is a read and it's all aligned. So some of this it's hard for the computer to call that's a variant. But at a certain frequency, based on probability, you can see that the gray one means it's what in the it matches the variant, the reference genome. Then the blue one is it occurs enough times for it to be called. All right. Then if you click on this one, you can actually get some details about it. Okay, so it says here that chromosome 5, this position, the reference is T, now it's changed to a C. All right. And then you can read this one. So it says down there, benign. So this one occurs at an earlier frequency is 50. That means one copy of this patient's genome was this, and that was T, and the other one was C. And it occurs at 0.5, half, right? It makes sense that we are diploid organisms. And people have noted that this one actually is a benign thing. It's just a normal variant. All right. So let's narrow down now by actually using the coordinate provided, because we narrowed down by the pathogen thing, right? So remember, we use a grep, look for pathogenic. So let me choose this coordinate. All right. And I put it into this one. So you can see I can specify chromosome, and then I just put the coordinate down there. Okay, so this is the one that is potentially pathogenic. Okay, let's have a look at the annotation. So this one easier to read. So it says here, multiple criteria, no conflicts. The disease is probably this, and please is probably Charcot-Marie-Tooth type 4C. And the funny thing about it is that the allele frequency is half-half, meaning that this patient has, because it's a germline thing, so he inherited the mutation either from the mother or father, we don't know. All right, and one of it is actually pathogenic. So let's have a look. Anything else in this thing? So there's a good consensus here that multiple people have submitted. There's no conflicts of the interpretation, and is likely to be pathogenic. All right. Let me see whether it's listed here. Can't find the thing here. It should be listed here, which is the molecular consequence. There it is. Okay, it's hidden here, hard for me to read. MC, it says it's a nonsense mutation, meaning that it just created a premature stop down there. And let's close this and have a look. So over here, let's zoom like that. Let's go back and let's see whether the calls are correct. So sometimes when we look, we just want to make sure that it's correct, because sometimes if the alignment quality or the reads down there are not very good, then you may say this is probably not a confident call. But this one seems to be okay. There's a few, half of it, you can see the green ones here, are called properly, and this is a high confidence variant call. All right. Then we can see this one is the coverage, meaning that if there are not many reads covering this region, it will be quite, like this part here is very low. Okay, this part here, they only got 1, 2, 3, 4 reads covering this region, so it's very low. All right. Whereas if you look at this, this pathogenic part, the coverage is pretty good. All right. So everything points that I'm quite confident that there's a real variant here. And based on the annotation, it seems as though multiple people have submitted, and it's a nonsense mutation. It's not common, and it is more, so I can be very more confident saying that this is probably the disease causing, one of the disease causing mutations. All right. Okay, let's go back here and then we can try the other one also. Let's see this one. So I'm too lazy to scroll, so I just copy and paste here so that I can go directly to that. Okay, so this is another one. Realignment looks pretty good. And you can see some of them are C's and whatnot. So to have all the information, I just click here. And it says here that it's a missense variant. Okay. And it is actually at the start codon, and it says here that it's likely to be pathogenic. So we're not sure yet. It's possible. Anybody? Okay, multiple submitters, no conflicts. Okay, so looks good. So I'm not sure. We can't narrow down for sure, but it seems as though 2 potential ones are that. So through bioinformatics like that, we can help in healthcare and like trying to give the patient some answer, because sometimes the condition you have no idea what, you can narrow down and find it. In some rare instances, there could be a drug that can be used to treat it. Okay, in many cases cannot, but at least you can, there is a resolution for that and actually can be used for counseling. So for example, this patient may want to start a family, and if you isolated the gene, you can actually give some indication of how likely this is going to occur. All right, should you start a family? All right, okay. So let me go back to that. And I think I end off by saying that there are many other ways to annotate. So we can use a web tool. So this is a nice one because I think people now are moving to get into 3D structure. Now, why is this important? Recall I said that there are many variants of unknown significance. You have no idea. If you look at the primary sequence, very hard to tell. So people have been trying to, let's say this is a protein sequence. And if you can map where the variant is, sometimes the vicinity of it gives you a clue. So for example, it is for hydrogen bond or ionic bond that holds a structure together. So if you actually mutate that one, you can predict structurally that something bad maybe happened that you cannot tell from the primary structure. So people have been trying to do this, and this one thing that we'll go through now. Okay, so the link is here. It's called VarMap. So this I can do it without the thing, just copy and paste the thing. So over here, all you do is just supply in this format. First is the chromosome, then the coordinate, then the original one, and then what you found. This one I found doesn't really work for us, so I'll just use this format. So let's go back to our thing and let's try the pathogen. Which one was it? Okay, let's try this one first. So I'm going to copy this, except this one is a problem. All right, because this one causes some confusion format. So I'll delete this column. So let me copy this first, and then where did I put it? Put it into VarMap, and I paste here. So I'm going to delete the number here. Oops, I deleted too much. Okay, deleted this ID here, which is causing VarMap to have some confusion. So I just delete here. Oh, sorry. And the problem is that it needs to be tab separated or what. So or space separated. So I just convert it to space because whenever I press a tab, HTML, it will go to the next box. So I'm having problems. So I just put it to a space. Then I choose the correct genome assembly. All right, and then I press submit. And let's hope it works. Okay, so it searches the thing. Everything that's pre-computed is there. Oh, results are done. Click and it says, okay, we did find something. There's a codon change here from CGA to TGA. So if you recall your molecular biology, TGA is a stop codon affecting this protein. And you can first see the further results. You just click on this and then you'll dive in deeper. All right, let me just make it big for. So very nice. It says in this protein, the 3D structure, it causes termination in this chain. All right, so it says it's most likely to be important in the protein's function. So later it will give you some other calculations. So one of the databases are using SVM, support vector machine, to try and predict whether it's deleterious or not. So this one is CADD. A group actually did some modeling and then use SVM to train and to predict whether a variant is likely to be deleterious. So this one we could have done it inside our container, but the database is too big, so I decided not to, because otherwise it's almost impossible to get started and we'll run out of space. Okay, so they also showed that what are the variants in this space here that have been detected with no consequence. All right, just as a comparison. All right, so there's some more calculation about whether it's likely to be disease causing or not. But I think and then they tell you that it's usually expressed in the brain and spinal cord, and it affects these organs here. And there's a few diseases associated with it. As I mentioned before, Charcot-Marie-Tooth disease, 4C, is one of the top candidates. Then later they have more data showing you the secondary structure and where's the likely point that is affecting it. All right. So in this case here, our 954. So our termination point is here, around here. So you can see that you chop off a lot of the domains. All right, so you can see that this not like. Then after that, it gives you the mapping of the 3D structure. So you can see that it's mapped to this residue here. So meaning that right after this coil here, alpha helix here, basically most likely it gets chopped off here. Then the rest of protein is no longer there. So from here, hopefully it'll just give you a sense that by combining not just the annotation, but mapping it to 3D structure will give you some idea of how we can interpret a disease. Now, we have just taken a very simple case. In many cases, it is hard to decide what to do. And it's even worse in cancer patients, all right? So we have taken what we call a germline thing, something that's inherited. And because it's inherited, you got one copy from mother, one copy from father. So when you call a variant, it's easier to call a variant. Whereas a cancer is a mix of different cells. And sometimes you have no idea whether the variant, if it's a very small proportion, is real or it's noise. All right. Okay. So, oh, good. It's 12:30. So I think we made it. Ah, good. Thank you. Okay. So I think, let me see whether I can stop this. Then I can look at some questions. Okay. So that was the last part of it. And we brought the data out so that we can use external tools. You can actually run this within the container, provided you have enough space. All right, so some people like it because it's a self-contained analysis system. And you have this notebook system. As you do analysis, you record what you did and things like that. And then after that, you export the HTML, then you have a record of the thing. So for example, you know, this is one of the efforts that we could work towards reproducible computing. So it's not just the people who work in a wet lab. So wet lab, I ran a wet lab last time, and then like very hard to write down which reagent and stuff like that, and people forget. And sometimes we don't know the exact composition, and we cannot repeat the experiment. But I think the same danger also occurs in bioinformatics. That will make it hard for people to adopt it to real life in clinics. So for example, if I use BWA, who says what version? We don't know what version. If I use a different version or different genome reference, you get slightly different coordinate, you get slightly different results. So it may not be reproducible. All right. So I'm hoping that a demonstration of not just variant calling, but using a notebook system may help in some ways for what we call documented and reproducible computing. All right, let me have a look at the thing. Okay, I have a lot of samples. How do you visualize a result for multiple VCF? Okay, that one is a problem. Okay, so multiple VCFs, there are browsers out there, for example, Nomad and things like that, which we don't install, that you could use. Okay, I don't think you can install it locally. That is the problem. Multiple VCFs. There's another company I like called Golden Helix, and I installed it called Genome Browser. Okay, quite nice. And actually, it's even more functional. You can, I think I've loaded quite a few, but how many are talking about multiple? You're talking like a lot, like population level, that becomes a headache. And that one requires some other tools that you may not be able to install locally. Okay, I'm doing RNA-seq analysis, running transcript. Why is my gene name empty for brain cancer? Okay, this one is a very specific question. That one, I think you have to take it offline and look at the case, because we don't know, because I run string time before. Okay, are you using HT's, what was the aligner? I think it's usually paired with HTS-seq or something like that. Why is the gene name empty? Okay, this one I have to look, because if okay, this one, if I recall correctly last time, if you do R, you basically have the transcript ID, but then you need to run it and combine it with the gene name. So this one you use, you need a bioconductor module to try and link these two together. Right. Yeah, this one, otherwise it's very hard to see. So typically it's all transcript ID. Okay, I can't answer that one too much now, okay, because without seeing what it is, but that's great, because I'm not the one supposed to be answering. I think we have a community here. Hopefully, as we get to know more each other, we can connect, and then we'll all help each other out. Bioinformatics, health informatics is so wide that no one person can know everything, all right? And I think I hope joining forces from MYBS in Singapore with Asif at AP Bionet, I think hopefully this will be a good start for our region. All right. So maybe I stop talking first. I ask whether Asif has anything to say.
Hi, Kenneth, thank you for that wonderful session. Hang on, let me close the door. Okay, so, right, thank you, Kenneth. You must be exhausted now, so I think that was really great, and we really have very good questions coming in, and I'm glad that you offered that poly, is it? Platform. So I was like surprised, where are you getting these questions from? Because they're not
poll
from
everywhere, yeah.
So that's good. Now, you mentioned something about the community, so I just wanted to quickly share something. If you can stop sharing your screen.
Okay, I think, okay, Ken.
Yeah, so I just want to let all of you know that, as mentioned by Kenneth about community, we do have a data science interest group on Telegram, where we have people from around the world who are part of the group, and we share events, related events, content, and also, I mean, help each other from time to time if there are specific questions. So if you need help, you may want to consider, taking a picture of this and connecting to the group and partaking in the group's discussion and asking your relevant questions over there, and hopefully somebody would be able to help. This is one of the ways. Of course, there are many other ways of getting help. This is one of the ways, and you may want to take advantage of this. So I've left this for a while, so you may want to take a photo or screenshot and join this at your convenience. So with that, I think, Kenneth, I think we have come to the stopping point. We may want to now hand it back to our MCs to wrap it up, and then we take a short break before coming back for the keynote session. Thank you so much, Kenneth.
All right, thank you very much, and feel free to just I'll leave the poll open. I may not be able to reply you. I'm not sure. Probably on the chat is better, because the poll EV is mainly one way. I see them and I answer verbally, but I cannot reply on the poll EV.
Right. A big round of applause. A big round of applause.
Okay. All right. Thanks very much. I'll shut down my video, and then let's go have something to eat. And luckily, I didn't overrun the time. Okay.
We'll let Farah
Thanks.
an announcement, and then we can take a break. Yeah. All
Okay.
right. Farah, back to you.
Okay, I'm back. So we have come to the end of the workshop, and we will take a 57 minutes break. We will resume at 1:30 p.m. All the timing are GMT +8. Do try to come in 10 to 15 minutes earlier so we can start sharp. The Zoom link for the keynote has been provided in your welcome letter, or you can refer the website for broadcast with TubeLink. Links are also provided in the Zoom chat box right at the top. Do note that it may not be the same link as the current workshop. Thank you.
All right, so we'll close it here and see you later. All right, please look at the links provided to you. Thank you. Bye for now.